Okay, so one of the main aims of this series of videos is to try and get a sort of better way of looking at mathematics. Basically, we want to learn enough category theory so that we can describe pretty much anything we want to in mathematics in terms of category theory, okay? Because we're learning that the things that are going on in set theory, the kind of machinery of set theory which is traditionally used to describe things in mathematics, can be described in terms of category theory. It can be described from this kind of higher viewpoint. And it's so beneficial to understand this because then we can sort of generalize all that machinery, we can understand how it fits together better. We can really kind of extract out the essential details of what's going on in mathematics. So essentially then, one of our goals is to build up enough understanding of category theory that it can become our new kind of primary language for talking about mathematics. Now, in order for that to be possible, one needs to understand quite a lot about category theory. In particular, the sort of elementary pieces, the basic machinery of category theory, the basic kinds of arrows, for example, was what I was describing in the last video. And in this video, I want to focus on the basic kind of small important limits and colimits which occur in category theory. So in particular, I want to talk about terminal objects, products, equalizers, initial objects, co-products and co-equalizers, because using them we can build up any limit or colimit, and by looking at them in detail we're going to get a really good understanding of how we can think about basic things in terms of category theory. And so we're going to be interested in things like the structure of these monomorphisms, how we can refer to subobjects, how we can describe such things in terms of arrows, how that kind of stuff can relate to notions like the equalizer, which gives us this idea of being able to kind of solve equations. So, I mean, basically, we're just going to look at a few theoretical ways that these simple kinds of limits and colimits fit together and play with ideas like monomorphisms. But the other thing we're going to do, and this is a theme that I want to try and run with quite a bit in this and subsequent videos, is we want to not just be talking about theory all the time, because one could lose sight of the ground. The other thing we want to do is to keep some kind of sight on the ground. We want to keep some kind of an eye to what these different concepts we're rolling out actually look like in important categories. Okay, so one thing we can always do is look back at the category of sets and think about what things mean in that context. But you know, that's just one example. We'd rather have a whole kind of large collection of examples that we can look at to see how these concepts of interest are working. And so the examples that we're going to look at mostly are of this kind of type. Okay, so for example, today we're going to discuss the product of one thing, and we're going to see, for one thing, what does a product look like in this category here, the category of functors from C to set, where C is some chosen category. Okay, so these kind of functor categories of this form, we've already seen quite a lot of them in this series of videos. So for example, we have the category of graphs, the category of dynamical systems, the category of functions, and there's many others. They're very interesting things. And so what we do as we unroll these concepts, for example, we're going to talk about products, and as we unroll these concepts, we're going to understand how they work in these kind of categories of functors from C to set. And this is a very interesting thing to do, and it gives us a lot more insight into how these things like, for example, equalizers work in a more general context than just in set. Okay, so in my last video about special arrows, I talked about an idea that can be very useful for understanding about certain definitions in category theory, particularly the idea of limits. And so this useful idea is the idea of generalized elements. And so a generalized element of an object is nothing more than an arrow into that object. So we might call this G here a T element of this object B, because it's an arrow from T to G. Now, the reason that this is kind of good terminology in the way it's generalizing something is that, like in set, an ordinary element would be an arrow into a set X from the terminal object. This would be a singleton set, okay? And so ordinary elements in an ordinary set, we could call them one elements if we like, because they are basically corresponding to arrows from this object one, this terminal object. But in other categories, of course, knowing about other kinds of elements of other types is useful. So, for example, in a graph, the edges in a graph would, if we have this graph here, which has a single edge, maybe we call this graph epsilon. Then if we have a graph X, then an arrow in this category of graphs into X we could call an epsilon element of X, and it would basically be pointing out an edge of this graph X. So this idea of sort of T elements is very useful, and we can use it to understand lots of important things going on in category theory. So one example is the idea of a categorical product. So just to very quickly recap what this is, the product of objects A and B is an object which we call A times B, together with these arrows, so-called projections, P1 from A times B to A, and P2 from A times B to B. Now, these things have to satisfy a certain property, and that is that for any object T with its arrows F into A and G into B, there has to exist this unique arrow, which I'm calling F comma G in angular brackets, such that P1 after F comma G equals F and P2 after F comma G equals G. So to say it quickly, a categorical product is something with an arrow into A and an arrow into B, such that for any other thing with an arrow into A and an arrow into B, there's this unique intermediary arrow which makes this diagram commute. So what does this have to do with the idea of generalized elements? Well, the real important thing in practice with a categorical product is it allows you to interchange between these two different types of arrows, okay? So what I'm denoting with this horizontal line is that there is an isomorphism. So if we have an object T with an arrow F into A and an arrow G into B, then we can use this sort of universal property of our categorical product to get this unique intermediary arrow, F comma G, which is going to be an arrow from T to A times B. Now conversely, if we have this kind of, or any kind of arrow from some object into A times B, then if we do P1 after it, we get an arrow into A, and if we do P2 after it, we get an arrow into G. So we can also go from arrows into A times B to these pairs of arrows. So what do we have? We have a way of interchanging between single arrows into A times B and pairs of arrows, one into A and one into B. So we can interpret this in terms of generalized elements. We can say that a categorical product has the feature that if we have these sort of two generalized elements, a T element of A and a T element of B, then that corresponds to a T element of A times B. And also we can go the other way around. A T element of A times B corresponds to a pair of a T element of A and a T element of B. And we get those individual T elements using these projection arrows of our product. So again, when I say a T element of an object, I simply mean an arrow into that object from an object called T. So we see that we can really think about what's going on for categorical products in terms of these sort of T elements. And this is very useful. So this is very useful. For example, in my video on exponential objects, I, maybe about halfway through when I started talking about general categories, I explained where the kind of ideas about the product of two categories comes from. And basically, we get at that kind of understanding by looking at this type of approach and noting that we can describe features of our objects in our category by what arrows there are into them. And then there's this sort of correspondence between this case here, where you have a sort of T-type element in A and a T-type element in B, and this case here, which is the corresponding case where you have a T-type element in A times B. Okay then, so what we want to do now is to understand how to calculate products in these categories of functors from C to set, where C is some category. So a good example of a category like this would be the category of graphs. So for example, we want to understand how do you calculate the product of two graphs. But there are many important categories like this: the category of dynamical systems, the category of simplexes, the category of functions. There's many interesting examples of these kind of categories of functors into set. And we want to understand how to work out categorical products in these cases. So how are we going to do it? Well, I think the best way to do this is to use the Yoni Dilemma, because using the Yoni Dilemma, we're really going to see exactly, we're not just going to understand what the products look like in this category. And I mean, the form of the products is actually quite simple, but we're really going to understand where it comes from in a fairly deep way. So we're going to use the Yoni Dilemma. Now, I did a whole video on the Yoni Dilemma. There's a lot to it, but I mean, it's often used as a sort of tool for calculation. Okay, so, but I mean, the Yoni Dilemma is often used as a sort of tool for calculation. So how could that be? I mean, it seems like a fairly abstract sort of result about relating natural transformations and the sort of E-type elements in some of the objects in this kind of category. And, you know, it seems fairly abstract. So how is the Yoni Dilemma used for calculation? Well, I think maybe the best analogy I can Well, I think maybe a good analogy, just an analogy, is coordinate transformations. So if you've done some coordinate geometry before, you'll know that there are several ways that you can sort of refer to a point on a plane. For example, the usual way is to say, well, there's an x coordinate and a y coordinate, and together they describe where a point is on the plane, how far across from the origin it is, and how far up from the origin it is. Now, there's another way of describing a point on a plane, which is to say how far away from the origin it is, and from a given line, how far do you have to turn to get the point you're interested in? So that would be like an angle. So we have these two different ways of describing points on a plane, these two different ways of sort of putting down coordinates on a plane to describe where points are. The so-called Cartesian coordinates and polar coordinates. In the polar coordinates, we say how far away something is and what angle it is away. It's kind of like the way that people point at stuff. Anyway, we have these two different coordinate systems for the plane, and there are others as well, but let's just think about these two. So which one of these coordinate systems is best? I mean, you can transform from one coordinate system to another one. I'm not going to go into details now, but it is possible, of course. There's an equation that can take in this way of expressing where a point is and change it into polar coordinates, and there's another way to go back again. So these are really sort of the way to transform between these coordinate systems is sort of like an isomorphism. There's a one-to-one correspondence between the descriptions of points over here and over here. Okay, so we can transform between these two different coordinate systems, and they give us two different ways to look at what's going on in the plane. Now, which one's best? Okay, and which one's best in this case, it really depends on what type of problem you're studying. So if you're studying some kind of geometry where everything is like rectilinear, aligned up with the origin, then probably using the Cartesian frame is best. If you're studying some problem where everything is symmetric about the origin, kind of rotationally symmetric, probably polar coordinates would work better for you. So, okay, what's this have to do with the Yoni Dilemma? Well, when the Yoni Dilemma is applied to understand things about set to the power of c, this category of functors from c to set, I think it's something akin to a coordinate transformation, okay? Because the objects in set to the power of c are these functors from c to set. So here's an example of a category which we could take as c. It has these two objects e and v and these two arrows s and v. And so when we do a functor from this into set, e gets sent to a set that we could call the edge set, v gets sent to a set that we could call the vertex set, and these two arrows get sent to functions, which we could think of as picking the source vertices and the target vertices. And then we can think of such a functor from C to set as a graph, and it has a load of edges, and each edge has a source vertex and a target vertex described by the liftings of these arrows. So basically we can think of the objects in set to the power of c as these kind of collections of sets, one set for every object of c, with these kind of functions between them, one function for every arrow of c. And that's kind of like a coordinate system, okay? It's very roughly speaking. I'm trying to draw analogies really, But I mean, that's one way we can basically describe what's going on in set to the power of c, is in terms of the kind of sets that objects get sent to and the functions that arrows get sent to under these kind of functors. And that's a kind of direct way of describing what's going on, really. Now, the Yoni Dilemma gives us another way of describing what's going on. Just like if we make this kind of coordinate transformation and go to polar coordinates, we have another way of describing what's going on in the plane. So the transformation that the Yoni Dilemma gives us is it says, well, there are certain functors called functors, and these correspond to certain objects in this category C, and we can describe the kind of bits and pieces in these objects, as in the kind of images of things in C under these functors, you know, like the edge set or the vertex set of a graph. We can describe those in terms of arrows out of these special functors, and we can think of the kind of transformations between our different objects in set to the power of C in terms of composing things with these arrows. And we can think of the kind of actions where we apply the kind of functions that correspond to these arrows in C being lifted. We can think of those kind of actions, for example, that would give us the source vertex of an edge. We can think of those as in terms of composing our arrows, which point out the bits and pieces of our objects by composing with this special arrow h to the power of s here. This is like a special arrow between these special kind of functor objects, which corresponds to doing this kind of s action, corresponds to doing this. So I've just thrown quite a lot of information at you there. It's difficult to summarise the Yoni Dilemma because there's so much going on in it. I'll have another pass at it and then I'll describe more systematically what I want to say. So basically, think about this category of graphs. Okay, here's a graph. This is a functor from this category C here to set. So it sends E to this set of these two edges. Our functor sends V to this set of three vertices, and then this arrow S is sent to this function that associates these edges with source vertices, and this T here is sent to a function which associates these edges with a target vertex. So okay, we have this graph. Really, it's a load of edges, it's a load of vertices, and there's this source vertex function and this target vertex function. That's what's defining the graph in some sense. And so, okay, here's an edge of this graph. Here's an edge A. Now, we can think of this simply as a member of the set G of E. Okay, so we think A is in G of E. But the kind of fundamental correspondence that the Yoni Dilemma tells us is that this A in G of E corresponds with an arrow alpha from hom E comma blank to G. Okay, so this hom E comma blank is a special functor, and as a graph it looks like this, a single edge, and this A here corresponds to this kind of arrow of this category, which comes from hom E comma blank to this edge A. So you can think of this alpha here as a sort of arrow-based representation of this edge. It's sort of shining out this edge from this sort of edge template, this fundamental particle in the category of graphs. So there's another one here which picks out vertices. So that's a very basic summary of the Yoni Dilemma. what is this hom e comma blank? Well, it's a functor from C to set. It sends a object of C to the set of arrows from E to that object. So for example, if we have an object W in our category, then hom e comma blank sends W to this set of arrows from E to W. And how does this hom functor work on arrows? Well, if we have an arrow F in our category, from an object W to an object V, this would be in category C, then hom E comma F, as in the lifting of this arrow F on the hom E comma blank, is going to be a function from this set of arrows from E to W to this set of arrows from E to V. And the way it works is that if we have an arrow K from E to W, then doing this hom functor, which is then doing this hom thing, which is just a function, then applying hom E comma F to this K is going to give us F after K, because that's going to be an arrow from E to V. So this is a function sending elements in this set to elements in this set, according to this diagram. So it's a very nice thing if you have some category you're interested in, like of dynamical systems or graphs or whatever. It's a nice thing to work out these hom functors, because usually they turn out to be important structures, kind of like fundamental structures that you can describe all the other structures in your category in terms of arrows coming out of these fundamental structures. So in graphs we're using this category, and we find that hom v comma blank is a single vertex and hom e comma blank is a single edge. I'm going to pick up speed a bit because I could talk about the Yoni Dilemma until the cows come home, but you know, I've already done a whole video on it, so I'm just going to go quickly so we can get to the applications. And if this is too fast, then you know, you can watch my video specifically on the Yoni Dilemma. So the fundamental correspondence in the Yoni Dilemma is this one, between elements of this set G of E and arrows alpha from hom E comma blank to G. Now, how does this correspondence work? Well, let's say we pick some element A in G of E. Okay, so in this example, it would be like picking an edge of G. Okay, but this is all in general, really. I'm thinking of a general functor G from some general category C to set. Okay, so how do we go from here to here? I mean, I'm saying this is an isomorphism, basically. So how do we go from something like this to something like this? Well, this picture is the key. This is a naturality square, because we're assuming that alpha here is a natural transformation from this functor from C to set to this functor from C to set. And so if we have an arrow S from E to V, then we ought to have that this corresponds to a kind of naturality square. Okay, so we can draw this stuff in yellow, and because alpha is a natural transformation, we know that alpha v after hom e comma s equals g of s after alpha e. So what we do next is we say, okay, we know that these are all functions, so let's think about how they work on elements. So can we pick an element of hom e comma e? Well, what is this? This is the set of arrows from E to E. And I don't usually draw identities these days, but I will now. So there's an arrow, which we always know is going to be present from E to E. It's the identity arrow of E. So we know that there's always going to be an identity arrow of E that I'm calling 1 of E. And then we can just think about how these functions work on that element. So if we go this way, we do alpha e on 1 of e, and that's going to give us an element of g of e. Well, why don't we fix that? Why don't we assume that that is a? Okay, we can pick this alpha e, so it sends this 1e here to a. And the interesting thing is that once we do that, the whole of the rest of the natural transformation gets fixed, and it all works out very nicely. Okay, so we'll set alpha e of 1 of e to be a. Now, if we do g of s, then we get g of s of a. Now, what about going the other way around? If we do hom e comma s on 1 of e, then using this kind of thing, where f equals s and k equals identity of e, we see that what we're going to get applying this function here is just s. Okay, and then when we do alpha v on this, we get alpha v of s. And so we know that alpha v of s equals g of s of a. So what? Well, the important thing here is that this actually, if you think about it, has completely determined our natural transformation, because if we want the v component of our natural transformation, that's going to be, and we can do this for any object v, so we want the v component, that's going to be this function that goes from hom e comma v to g of v. And so to know how this function works, we need to know how it works on general elements of this set here, hom e comma v. Well, what's a general element in that set? It's just an arrow s from e to v. And here we know that for an arrow s from e to v, doing the v components of this natural transformation alpha gives us g of s of a. And so this tells us how this arbitrary v component of our natural transformation works. So just by fixing this a here, the whole way that this natural transformation works is fixed. And so that's how we go from here to here. How do we go from a natural transformation alpha back to an element of a? Well, that's easy. We just set a is equal to alpha e of 1 of e. Okay, for example, here we have this alpha here that's our kind of arrow based, or need a base way of describing this edge, and to recover the actual edge back again, we just do alpha e operating on identity of e, and we get this edge back again. So that's our fundamental correspondence in this Yoni dilemma. Now there's two other kinds of relationships which are quite easy to get at now we have this, which are very important for actually using the Yoni dilemma. I mean, again, think about the coordinate transformation idea. If you want to do a coordinate transformation, you better understand how it works in general, okay? So you can really go from this way of looking at things to that way of looking at things in totality. You don't want to have some holes in your understanding. And in a similar way, we want to go from this kind of set-based way of thinking about these objects in this category to this kind of arrow-based way of thinking about it. And we better understand how we can change, and we better understand how we can talk about all of the goings-on in this category in terms of arrows. Otherwise, why would we want to use this other viewpoint? We now understand this kind of fundamental correspondence between the kind of E-type and elements associated with these functors, and these kind of arrows into these functors from hom e comma blank. I mean, these arrows in this category, they're really natural transformations. But we want to know how to talk about two particular things. One of them is, how do we talk about a natural transformation from one of these functors, g, to another one of these functors, g dash, to say a natural transformation phi? we know how to think about that in terms of the kind of E-type elements and V-type elements and so on of these functors. How do we think of it in Yoni terms? How do we think of it in terms of these arrows? And this is really the fundamental relationship between, this is another kind of isomorphism. So we suppose we have some A, which is just an element of G of E, and we have this natural transformation phi from G to G dash. And we want to understand what it means to do this natural transformation and how it's going to transform this element A. We see on the diagram that A is going to get sent to phi of E of A, which is going to be here in this case. But how does this work in general? Well, in general, this element here of G dash of E that we get by applying phi of E to A is going to correspond in arrow speak to this arrow phi after alpha, which is going to go from hom E comma blank to G dash. Okay, how can we see this? Well, we know we have this sort of correspondence between these elements of G of E and these arrows. So here's an arrow from hom E comma blank to G dash, this arrow which is phi after alpha, and let's just see what this corresponds with. So we know that the element of G dash E that this corresponds with is going to be phi of E after alpha of E operating on identity of E. And we know that this alpha of E operating on identity of E is just going to be A. So yes, this is going to correspond with phi of E of A. Okay, so we see just using this correspondence, which we know about, that these two things correspond with each other properly under our chosen kind of isomorphism between elements of G of E and these arrows. So that's good, because basically it means that we can think about these natural transformations without having to always think about what their components are and how they're working on the stuff in the sets and all that. In graphs, for example, we can just think, well, this edge is described by this arrow alpha. If we apply this natural transformation, we want to find out what happens to this edge, we just compose phi after alpha, and that's going to point out the edge we want in G dash. Okay, so that's one thing. The only other thing we need to know is what happens when you do this sort of S action on a particular object. Okay, so what do I mean by the S action? Well, let's say we have this edge here, A, in this graph G, and we want to work out what's the source vertex of it. So the usual way to do it is to say, well, I know this is a functor from C to set. I know that A here is an element of G of E, the thing that this object got sent to under our functor. And I know that G of S is this function, and if I apply G of S to A, then I'll get this vertex V, which is the source, then I'll get this vertex, which is the source vertex of A. So that's the kind of element-centric approach. So that's how we describe this process in terms of elements. But when we apply this kind of Yoni isomorphism, and you're thinking about things in terms of arrows, the way we describe this is really quite different. So in general, when we have a category of functors from C to set, we may have an arrow S from some object E to some object V. Now, we know that there's going to be a functor hom e comma blank corresponding to object E, and we know that there's going to be a functor hom v comma blank corresponding to object V. Now it turns out that this arrow S from E to V has a kind of corresponding arrow connecting these associated hom functors. But the funny thing about it is that it actually goes in the opposite direction. Okay, so here S is an arrow from E to V, but the corresponding thing is this arrow H, well, I'm calling it H to the power of S, which is an arrow from hom V comma blank to hom E comma blank. So this goes from E to V, this goes from hom V comma blank to hom E comma blank. It goes in the opposite way. And I'm just calling this H to the power of S, but this is just sort of notation to remind that this arrow is associated with S. There's nothing directly related to exponentiation or anything here. This is just a way of recording that this arrow here has something to do with S. So what is this H to the power of S? Well, it's a natural transformation from hom V comma blank to hom E comma blank. And how is this natural transformation defined? Well, the xth component of H to the power of S ought to take us from hom V comma x, the set of arrows from V to x, to hom E comma x, the set of arrows from E to x. So how do we do it? Well, let's say we have an arrow m from V to x. Well, this function here, the xth component of this H to the power of S thing, it sends this m to m after s, which is indeed an arrow from E to x. Okay, so that's what this H to the power of S thing is. And the cool thing about this H to the power of S thing is that composing some arrow alpha with it is corresponding to doing this kind of S action on one of these E-type elements. So when I say doing the S action on one of these E-type elements, what I mean is this. Think about an element A in G of E. Okay, this is just a set. So I might call this A an E-type element of G. Okay, like an edge of this graph G, for example. Now, when I say doing the S action on that A, I really mean we have this arrow S from E to V, and when we lift this under our functor G, we get this function G of S. That's a function from G of E to V of E. And when I say doing the S action on A, I mean calculating G of S of A. We have this arrow S from E to V. It lifts to become this function G of S, and when we apply it to A, I think of that as doing this S action on A, and that's going to give us a V-type element, an element of G of V in general. Okay, I know the notation corresponds with graph speak, but I'm talking in generalities with all these formulas. This is just an illustrative example. Okay, anyway, here's the fundamental correspondence that this thing we get by taking our E-type element and doing this S action on it, this G of S of A, this is an element of G of V, but what arrow does this correspond with under our kind of Yoni correspondence? Well, the key thing is that it corresponds with alpha after H to the power of S. Okay, so for example, here we pick this edge A. It's represented by this arrow alpha from this hom E comma blank to G, and then if we do alpha after HS, those composed is just picking out the source vertex of that edge. Okay, so this is one way to talk about the source vertex in terms of elements, and this is the arrow-based way of doing it. So how can we see that this is true? How can we see that alpha after h to the power of s corresponds with g of s of a? Well, we just do a similar thing to what we did up here, okay? We just say, well, let's take alpha after h to the power of s. So that's one of these arrows, okay? And then we want to know which element this corresponds with. So just like we take in natural transformation alpha, and then we take the appropriate component operating on the identity, we get the proper element, the kind of element that this corresponds with. So we'll do just the same thing here. It's just that here, alpha after h to the power of s is a natural transformation from hom v comma blank to g. Okay, so we want to take the vth component of this natural transformation and operate it on the identity of it. Okay, we get alpha v after h to the power of s of v operating on identity of v. So what's h to the power of s of v operating on identity of v? Well, we see how this function associated with the component of h to the power of s works. And so we see that if this m was an identity, then the output would just be an s. Okay, so we know that this evaluates to be an s. So we have alpha v of s. And then we just look up here. Oh, look, alpha v of s is g of s of a. So this is g of s of a. And that's just what we wanted. Okay, we wanted to show that alpha after h to the power of s corresponds with g of s of a. So now we have all the components we need to work with the Yoni dilemma. We know how we can describe the E-type elements or the V-type elements or whatever. We know how we can describe the S actions, and we know how we can describe doing these natural transformations and transforming from one structure to another. Now we have all this stuff, we can apply it to get a very kind of direct understanding of how categorical products work in this category of functors from C to set. Okay, so what we want to do now is to apply the Yoni dilemma to determine the product of two objects in this category of functors from C to set. So once again, we can imagine we're thinking about two graphs, just so we have something concrete to deal with. And just to kind of give away the punchline, I've shown a result of doing a categorical product of this graph here, x, and this graph here, y, and it's drawn here. So we can see that the result is pretty simple. For example, the vertex set of this graph x times y is just the Cartesian product of the vertex set of x and the vertex set of y. It's a similar situation for the edge set, and we have that this, for example, this 2, 1 dash, this is the product of this edge 2 of x and this edge 1 dash of y, and its source is the kind of pair of the sources of 2 and the sources of 1 dash, because the source of 2 is e and the source of 1 dash is g, so the source of 2, 1 dash is g, e. So if you think about this for a while, you'll understand what I mean when I say that basically when we take the categorical product of a pair of objects in set to the power of c, things are working pretty much the same as when we're taking products of sets, but just component wise. So for example, the way that this product thing works on edges is pretty similar to the way that you would take the product of sets. I mean, when you take the product of sets, just forgetting about this to the power of c, all you do is take the Cartesian product of those sets. And it's a similar situation here, except we have many components. We have a component for edges and a component for vertices when we're talking about graphs. And when we do the action on something, when we do the S action, we just do it on the elements pairwise. Okay, so if you have a pair of, like, an edge in this product, x times y, is a pair of an edge from x and an edge from y, and when we find the source of this, that'll be the pair of the source of this edge in here and the source of this edge in here. So that's a very short summary of the result we want to get at. But now we want to actually arrive at that in a systematic way using this Yoni Dilemma. Okay, how are we going to get at all these results? Well, we're going to use the Yoni Dilemma. So I've summarized the important kind of formulas and relationships from the last board full of writing in this purple bubble here. And now we're going to think about the categorical product. So I know I do this in almost every video, but let's just remember what it actually means. So categorical product of x and y is this object which we call x times y with these arrows, P1 and P2, P1 going into x and P2 going into y. I'm using superscripts here just to label things. These have nothing to do with exponential objects or anything. They're just a convenient way to label stuff so that one doesn't get confused, because these are arrows and natural transformations, and I don't want it to be confusing that, you know, these look like components of natural transformations or whatever. So we have these projections, p to the power of 1 and p to the power of 2 into x and y, such that for any object t with an arrow f into x and g into y, there exists a unique arrow f comma g, which makes this diagram commute. Okay, that's the familiar definition of the categorical product. Now we want to determine the categorical product of x and y, where x and y are functors from C to set. So how do we do it? Well, we basically use the Yoni Dilemma. So there's sort of two fundamental transforms that we're going to use. This Yoni Dilemma, where we can transform from an E element A of G to an arrow alpha from HOM E to G. And also we're going to use this kind of isomorphism here, where we can go from a pair of arrows, F comma G, from T to X and Y, to an arrow F comma G from T to X times Y. Okay, remember we talked about this at the beginning. We can convert between these two because given this, we can do P1 after it to get F and P2 after it to get G. And we can go from here to here using this universal property. So, okay, that's great. Now let's understand what we mean by an element A of type E in X times Y. In other words, what's it mean for us to have an element A of X times Y of E? Okay, because this is just going to be a functor from C to set, and so X times Y of E is going to be what X times Y sends E to, and there's going to be and that's going to be a set, and it's going to have elements. But how can we think about those elements? How can we construct this set? Okay, that's what we really want to do. We want to find out, for example, in graphs, we want to find out what's the edge set of this graph and what's the vertex set and so on. But I'm talking in generality here. This is for any case where we have functors from some category C to set. So we have this A in here. Now we use the Yoni Dilemma. So this becomes an arrow alpha from HOM E comma blank to X times Y. Now, given any arrow alpha like that, I mean, imagine this T here is HOM E comma blank, and this green arrow is alpha. Well, if we do P1 after alpha, we get the sort of first component of this arrow. And if we do P2 after alpha, we get the kind of second component of this arrow. So let's call the first component alpha X and the second component alpha Y. So in other words, we're supposing that, space left to right, we are supposing, maybe I can write here, that P1 after alpha equals alpha to the power of X, and P2 after alpha equals alpha to the power of y. Once again, I'm using these to the power of just as notation. Okay, I'm just labeling these, saying somehow this has to do with alpha and it has to do with x. And I'm just using a superscript to denote that for no concrete reasons. So it's just part of the name, nothing to do with exponential objects at all on this board. So because we're supposing this, we can actually think of this alpha here, we can actually write it with these angle brackets as alpha x, comma, alpha y. We can think that this arrow alpha from hom e comma blank to x times y it consists of, it can be written as this pair, you know, it can be thought of as the intermediary arrow associated with alpha to the power of x and alpha to the power of y. So it's like this picture here where we're calling this alpha. Whoops. Where we're calling this alpha. Just forget about this part of the picture for the time being. Okay, so fine. We have this arrow alpha from hom e comma blank to x times y, and then using the kind of categorical product isomorphism, or whatever you want to call it, we see that this corresponds to an arrow alpha x from hom e to x and an arrow alpha to the alpha y from hom e to y. And then, so we have a pair of arrows represented in this line, and then all we do is we apply the Yoni isomorphism again. We go like this way. Okay, so this alpha to the power of x then corresponds to something we might call a to the power of x, which is going to be an element of x of e. And this alpha to the power of y corresponds to an element that we might call a to the power of y in y of e. So basically we see that this element a of x times y just corresponds to a pair. A pair of elements, one from x to the power of e, which we call a to the power of x. Again, to the power of doesn't really mean anything, it's just a name. And then the other thing being this element of y of e, which we call a to the power of y. And so then, since these elements of x times, since these e-type elements of x times y just correspond to these pairs here, we might as well really think of this a as, we might as well actually just call it a to the power of x, comma, a to the power of y. Because it really is just corresponding to a pair of an element of x of e and an element of y of e. Okay? And if you think about it, this is just what we do in the category of sets. We actually think of the elements of the categorical product as these kind of pairs. Okay, so the long and short of it is that the E-type. So the long and short of it is that the set of E-type elements of the product of two objects is just the Cartesian product of the E-type elements of each of those objects. Okay, so the edge set of x times y is the Cartesian product of the edge set of x and the edge set of y. And similarly for the vertex set. So that's good, we're making progress. Now we understand what the kind of E-type elements are in this product. The next thing to understand is how the projections work. So let's say we have one of these E-type elements, ax, ay of x times y. So let's say we have one of these E-type elements, ax, ay of x times y, and we want to do this projection on it. Okay, so it's an E-type element, so we want to take the ETH component of, let's say, this first projection, and we want to do it on here. Well, I think you can guess that the result here is just going to be a to the power of x. But how do we get at this result? Well, firstly, we use this result here. And this, because this p to the power of 1 here is just a natural transformation. And we see here, where is it again? Here, yeah. We see that when we do the eth component of a natural transformation on one of these e-type elements of G of E, this result in the Yoni language corresponds to phi after alpha, where alpha is the kind of arrow that corresponds to this element A here. So using this, we have that doing this on this corresponds to doing P1 after the kind of arrow corresponding to this element AX, AY. Well, we see that that arrow corresponding to AX, AY is alpha X, alpha Y. So this element here corresponds with this arrow, which is P1 after alpha X, alpha Y. And we can just evaluate this because we know what this composition is. It's just alpha to the power of X. And then going back again like this from arrows to elements, we see that this just corresponds to a to the power of x. So yeah, projections work just as you'd expect, just selecting the kind of, well, this would be P1 would be selecting the first element, and it works kind of component wise on edges and vertices and, you know, E-type elements in general and so on. And similarly, P2 would be selecting the second entry in these element pairs. So that's fine. Just one more thing we need to understand then is how do S actions work on this stuff. So let's say that we have this pair AX, AY. This is an E-type element of X times Y. And we want to do an S action on it. Okay, so we have this arrow S from E to V in our category C, and we want to do X times Y of S operating on this element AX, AY. In other words, we want to do a sort of S action on this. For example, in graphs, we want to say find the source vertex of this edge, okay? So how can we understand this? Well, we use this kind of result here, okay? So it says that when we want to do an S action on an element, an E-type element, that corresponds in kind of arrow language or Yoni language to taking the arrow alpha corresponding to the A and doing that arrow alpha after h to the power of s. Okay, so that's what we do. We get the arrow which corresponds with AX, AY, that being alpha X, alpha Y, and then we do that after h to the power of s. And this arrow here is the arrow corresponding to this element here when we use the Yoni isomorphism to go from elements to arrows. Now we can use a result which I think I discussed in my video on exponential objects. It's a very useful result that when we have a categorical product and these arrows, and we have like an arrow with angle brackets after another arrow, we can always rewrite this by just taking two copies of this arrow on the right inside the angle brackets. So we can rewrite this as alpha to the power of x after h to the power of s, comma alpha to the power of y after h to the power of s. And so now, of course, this corresponds to a pair, an arrow alpha to the power of x, h to the power of s from hom v comma blank to x, and an arrow alpha to the power of y, h to the power of s from hom v comma blank to y. And for those two individual arrows, we then go back again from arrow speak to element speak, and we see that this first arrow here, which is like this, corresponds to x of s of a to the power of x, again under this kind of correspondence. And similarly, alpha to the power of y, h to the power of s corresponds to doing the s action on a to the power of y in y here. So we can see that basically doing the s action on this pair of elements gives us the pair of things that we get when we've done the s action on the individual first and second entries in the pair. Okay, so for example, the source of 2, 1 dash is the pair of the source of 2 and the source of 1 dash. So that's it. That's pretty much a summary of how to do categorical products and how that's kind of inspired by the Yoni Dilemma. And if you want, you can basically do the same thing for general limits. And it's a very interesting exercise. You can basically reason out all the features of how, like a limit of a kind of diagram in set to the power of c, how its structure comes about as a sort of result of the Yoni Dilemma. Okay, so we want to talk about more important results, which have to do with subobjects and monics. And the kind of style I want to go for with these videos is that as we keep building on these concepts in general kind of categories, we also have this sort of more practical element in our understanding, which is basically how all this stuff works in this category of functors from C to set, because there are many of these different kinds of categories of functors, like graphs and dynamical systems and so on. And if we understand how to describe all of our concepts of interest in arbitrary categories of functors from C to set, then we can generate lots of examples and make sure we understand what's going on with all these cases we're studying. So it seems important then to get a thorough understanding of what a monomorphism is in this category of functors from C to set. So remember, an arrow in this category is just going to be a natural transformation. So for example, this graph is corresponding to a functor from this C to set, and so is this graph, and this arrow alpha from this graph to this graph corresponds to a natural transformation from the functor that makes this to the functor that makes this. So for example, let's consider an object G and an object G dash and an arrow zeta in this category of functors from C to set. Well then, G and G dash are both going to be functors from C to set, and this zeta is going to be a natural transformation between them. So for every object E, there's going to be a sort of ETH component of this natural transformation going from G of E to G dash of E. And these are sets, and so zeta E is going to be a function, okay? So the sort of ETH component of this arrow from G to G dash is a function sending E-type elements of G to E-type elements of G dash. So that's a little bit of background about what the arrows in this category look like in general. Now, which arrows are going to be monomorphisms? Well, I mentioned this result in the last video, but I want to actually go for a proof this time. So the claim is that the arrows in here, which will be monomorphisms, are the natural transformations, are precisely the natural transformations which have each of their components as a one-to-one function. And we see that this is just a direct kind of generalization of the case in the category of sets. In the category of sets, one-to-one functions and monomorphisms were exactly the same thing. In this case, the monomorphisms are the natural transformations which look like one-to-one functions on each of their components. Okay, so let's be a bit more precise about this. Let's consider an arrow f from A to B. Now, there's two claims that I am saying are equivalent. One of them is that f is a monomorphism, or otherwise stated as another way we can say that is f is monic. Okay, this means f is a monomorphism. And the thing I claim is equivalent to that is this statement that for each object E in this category C, we have that the eth component of f, which is going to be a function from A of E to B of E, is a one-to-one function. Okay, so I claim that these two statements are equivalent. So how can we see this? Well, let's start by showing that f is a monomorphism implies that it's one-to-one on each of its components. Okay, so we'll suppose that f is a monomorphism. Now let's consider a couple of elements A and D of A of E. Okay, so these are a couple of E-type elements A and D of A here. Well, using the Yoni Dilemma, we can find that these two E-type elements of A correspond to arrows, alpha and delta, from hom E comma blank to A. Okay, so think about, for example, selecting edges in a graph. So now the thing is that we want to show that this f here, we want to show that each of its components is one-to-one. So let's consider the eth component. Of course, this argument works for any capital E, but we'll consider the eth component operating on A, and let's just suppose that f of E of A equals f of E of D. Now, the definition of being one-to-one on objects is that fe of A equals fe of D implies A equals D. So what we want to do now is to show that this assumption here implies that A equals D. So how do we do it? Well, what we do is we then think, okay, let's use Yoni again. In particular, let's use this one, which has to do with how this kind of Yoni correspondence between elements and arrows interacts with doing a natural transformation on our data. Okay, so what this says is that doing the eth component of phi on A corresponds in arrow language to doing phi after alpha, where alpha is the arrow corresponding to A under this kind of Yoni isomorphism. And so for us, what this means is that if alpha is the arrow corresponding to A, then f of E of A corresponds to f after alpha, and f of E of D corresponds to f after delta. And since these two are equal, it must be that these two are equal. But now, since we're assuming that f is a monomorphism, what do we get? Well, we get that alpha equals delta. Okay, so these arrows have to be equal. And now we just use Yoni again to convert back into element speak, and we get A equals D. So we do indeed have that f of E of A equals f of E of D implies A equals D. Therefore, f of E is a one-to-one function, taking us from A of E to B of E. And this works for any object E of the category C. And therefore, we're done. We've shown that if f is monic, then each of f's components are one-to-one functions. So we're done going from here to here, but we want to argue the opposite way around now. We want to suppose that f is one-to-one on each of its components, and we want to infer now that f is monic. So this is this argument down here. So how does it go? Well, we'll suppose we have an arrow f from A to B, which is 1 to 1 on each of its components. So for every object E of C, we have that the eth component of f, which is going to be a function from f of E to B of E, is a 1 to 1 function. Okay, and now let's take any object T and any pair of parallel arrows, psi and phi, into A. Now, we want to show that f is monic, so we're going to assume that f after psi equals f after phi, and we want to infer that psi equals phi. So how does it go? Well, firstly, this assumption means that if we pick any capital E, any object in C, then, since these two arrows are equal, their eth components must be the same function. So we must have that f of E after psi of E equals f of E after phi of E. And since these functions are equal, they must work the same way when we give them an input. So let's give these functions an input, a little e, which is going to be an e-type element of t. Then we must have the fe psi e of little e equals fe phi e of little e. So little e here is a capital E type element of t, and doing phi e of it will give us a type capital E element of A. So that's what psi e of little e will be. Similarly, phi e of little e will be another capital E type element of A. And so let's give these names. Let's call psi e of little e, let's call that u. So u is going to be one of the E-type elements in A. And also phi e of little e, let's call that v. That's going to be another type capital E element of A. But the thing is that we're assuming that the eth component of f is a one-to-one function on these type E elements. So that means that we have that fe of u equals fe of v implies u equals v. Well, with these substitutions, that's what we have. Fe of u equals fe of v. So we must have that u equals v. So we've got this now. And this is pretty much what we want, because this argument holds for arbitrary little e, because this argument that psi e of little e equals phi e of little e, this holds for any little e in t of capital E. Okay, so that means that we must have that psi of e equals phi of e, because these are just functions, okay? And if the functions agree for any element they might act on, then we must have that psi of e equals phi of e. And also, this argument holds for any object E of this category C here. And so we must have, in fact, that psi equals phi, because we can apply this argument for any component to show that the kind of functions corresponding to the natural transformations along those components are equal. So we have basically that f after psi equals f after phi implies psi equals phi. So that means that f must be a monomorphism. Okay, so what is a subobject of a graph? Well, it's a subgraph, right? So what's a subgraph? Well, we have some graph, and if we pick a subset of its vertices and a subset of its edges, do they make a subgraph? Well, not always, right? Because there's more to a subgraph than just being a subset of the vertices and the edges. They have to actually make a graph. Okay, so for example, if we pick one of the edges, we better pick both of the source and target vertices of that edge to be part of our subgraph, so that it really does form a graph. So in other words, we can think of a kind of subgraph as a set of vertices and a set of edges which themselves form a graph. And another way to say that latter statement is that those subsets are what we might call closed under actions. So if we pick an arrow S of C and we do the S action on our edge set, that should give us something on our chosen vertex set. And similarly, if we do the T action, we ought to get something back. So this suggests a nice simple way of thinking about what monics look like in this category of functors from C to set. I mean, an object in this category, we can think of it as a set. So an object G in this category, we can think of it as a set G of E for each object E, with these kind of lifted functions between. And then if there's a monic going into such an object, we can think of that as selecting subsets of these sets G of E in such a way that these G of S functions always sort of send one of these subsets into another one and so on. It's closed under these actions. So this is the kind of picture of how monics work that I want to get across. So the first thing I want to talk about is inclusion functions. Okay, so the idea of inclusion functions helps to sort of simplify thinking about subsets in set, for example. So let's say we have a big set here, and in this set we have this subset holding 1 and 2. So let's call that subset X, and let's call this big set B. Well, then there's a function from X to B which sends 1 to 1 and it sends 2 to 2. That's called an inclusion function. So the inclusion function is a function from X, where X is considered as a set, to B, and it doesn't alter the names of the elements in X, it just considers them to be members of this larger set B. Okay, so we use this kind of arrow with a curled tail to denote an inclusion function. So IE here is an inclusion function from X of E to B of E. So if we have an object X and an object B in this category of functors from C to set, and we write a sort of arrow with a curled tail like an anchor, like this I thing here, we mean that this is a arrow of our category of functors which has each of its components as one of these inclusion functions. Okay, so the way that we can think of this X here is that for every type E, for every object E of category C, we can basically think of X of E as being a kind of subset of B of E. But we're doing category theory, we like to put everything in terms of arrows. So rather than just saying X of E is a subset of B of E, we say, well, we have this inclusion function that sends X of E inside B of E. So the first thing I want to get across is that this I here, described like this I here with this description, is actually a monic. Okay, and it's fairly easy to see that this is a monic because I've already demonstrated that an arrow being a monic in this category is equivalent to that arrow being a one-to-one function on each of its components. Okay, because arrows in here are natural transformations, they have components for the different objects in C, and an arrow is going to be a monic if and only if each of those components is a one-to-one function. So all I have to do is show that I of E is a one-to-one function for an arbitrary object E of C. And that's fairly easy. If we take a couple of elements A and D in X of E, and we assume I of E of A equals I of E of D, then, well, since this is an inclusion function, it's trivial really. This is equal to A and this is equal to D, so A equals D. So this implies A equals D. And that's enough to show that I of E is one-to-one on these kind of E-type elements. And since this happens for every component E of our natural transformations, that shows that I is monic by this previously argued correspondence between monic arrows and arrows which have each of their components as one-to-one functions. Okay, so great. We have these special kinds of monics that we can make. So, I mean, the basic top and bottom of what this first statement's saying is that if we have a functor x from C to set, and the kind of E elements in it are all stuff that's just contained in the set of E elements of B. In other words, if this X really looks like a substructure of this B, then this inclusion function, which really just takes this structure and considers it to be part of this larger structure without altering the names of anything, this I is going to be a monic. Okay, so that's fine. But how does this help us understand what ordinary monics are? I mean, there's lots of monics in this category of functors from C to set, and surely they're not all inclusion functions. Some monics do more complex things, like they sort of change the names of elements and things like this. So how can we think of those? Well, the point is that every monic in this category from C to set actually is equivalent to one of these sort of, I may call it a kind of inclusion monic, these kind of monics that have each of their components as an inclusion function. So the great thing about this is then that given any monic f from any A to B, we can find something equivalent to this, which is basically acting as a kind of inclusion arrow, okay, which has this nice simple structure. So up to equivalence, every monic might as well be one of these inclusion arrows. So this is fairly important, and I'll go through the argument for this now. So let's suppose we have a monic f from A to B. And basically what we want to do is cook up a kind of diagram like this, okay? So we have this monic f. We want to find this kind of inclusion monic I, which is equivalent to f. Okay, so there's these arrows back and forth, and this would be a commuting, well, the two triangles we can get would commute anyway. So we'd have f after r equals I, and I after f star equals f. Okay, so this is what we want. But how are we going to do it? Well, the first thing we need is this x. So how are we going to find this x, which is a inclusion? So we'll want to find this x, which is basically something like a kind of substructure of B, so that we only need this kind of inclusion monic to go from x to B. So how do we do it? Well, for any object E of our category C, we set x of E to be the set of elements of B of E, such that there exists an element little a of A of E, such that doing Fe on A equals B. So in other words, this is the set of E-type elements of B that have something sent to them under the ETH component of F. Okay, so this is like the like looking at the ETH component. This is the stuff that has stuff sent to it under F. Okay, I might also add that we could say here there exists a unique A, because we know that f of e here is 1 to 1. It's a 1 to 1 function, okay? So if there is some a such that f of a equals b, there can only be one such little a. There can't be more than one different one, but because we don't have f of e sending distinct elements to the same element, that doesn't happen. So sometimes this exclamation mark's used and this is read, there exists a unique element a such that f of e of a equals b. And that uniqueness is going to help us later. So anyway, this tells us then how we form x of capital E for every object E. But we also need to understand how arrows of C get lifted under this functor x, because we're trying to make a functor x from C to set. Well, let's just define x of s such that for every little b in x of E, we have x of s of b is equal to b of s of b, little b. Okay, so this holds for any little b in x of E. Now the idea here is simply that we're selecting the E-type elements of x to just be the E-type elements of B that have stuff in A sent to them under this monomorphism F here. And then we want the S action on these elements to look like the same way the S action looks in B. So it'd be like if you were selecting a subgraph, you'd select all the vertices and the edges, and you'd assume that they're connected up the same way that they were in the superstructure. Okay, so this is how we define x of s, and this is of course only defined on the b in x of E, because this ought to be a function from x of E to x of v if s is an arrow from E to v. So we can think of this as sort of, we can think of x of s as sort of a restriction of b of s restricted to operate on these elements in this subset x of E. Okay, but how do we know that x is going to be closed under this s action? How do we know that doing x of s on some element b of x of E is going to give us an element of x of v? I mean, it's like this issue of a graph, right? If you select an edge in a subgraph, you better select the source vertex and the target vertex, so you do get a real graph. And in a similar way, we want to be sure that if we do this S action on an element of x of E, we get something in x of v. We do get that. We get that automatically by the kind of naturality, by the fact that f here is a natural transformation. So let's see that. What happens if we do x of s on b? Well, doing x of s on such a b, we can write that instead as doing b of s on such a little b. And for such a little b, we know that there exists this unique a such that f of e of a equals b. So we can replace this little b with f of e of a. And now, if we think of a little a in this set here, then we can think of this b of s of f of e of a as the result of doing these functions starting with this little a, like so, going around this naturality square. And by the naturality, this is going to be equal to f of v of a of s of little a, like so. And now we can see that this must be in x of v. Why? Because there is an element of a of v in particular a of s of little a, which is such that f of v of this element gives us this thing. And if you think about how x of v would be defined by an equation like this, the existence of something in A that gets sent to it, the existence of something in A which gets sent under the appropriate f function to our element of interest implies that our element of interest must be in capital X of V. So this shows that this kind of x defined like this is a properly working member of, so this shows that this x defined in this way is a proper object of set to the power of c, because it has well-defined E-type elements and it has a well-defined action. I mean, to rigorously establish this, one probably has to do a few more steps, but hopefully it's clear that we can define x in such a manner. Okay, so we have this object x. Now, how does this inclusion function work? Now, how does this inclusion arrow work, this I? Well, it works just like it did up here, okay? We define x of e to basically be a subset of b of e. And the eth component of I is just an inclusion function from x of e to b of e. Okay, so we understand what this I is. Now, what about these other two arrows? So, I mean, what we really want to do is we want to show that f is equivalent to I. Okay, so basically we want to show that I is contained in f and f is contained in I. Okay, because we know these are both monics. And so we'll do this in a component-wise way, because we've already seen that we can argue about these monics in this kind of component-wise way. So what we basically want to do is to cook up these arrows R from X to A and F star from A to X. And we want that F is equal to I after F star. So F is in I. And we also want that I is equal to F after R. So we have F is contained in I and I is contained in F. Okay, these are the equations we want, but let's get them for the eth component. So what we'll really go for is we'll prove this component wise. So we want to come up with this R and F star such that for any component E, for any object E of C, we have FE equals IE after F star E and IE equals FE after RE. So that's what we're going to go for. Now, there's a couple of different cases that we want to understand. One of them is where one of these two sets here, when we're looking at the eth component, is empty. Okay, so imagine we're looking at the eth component of this diagram. So I could put e's everywhere, but I won't bother, you can imagine. Now, the thing is that let's say that A of E is the empty set. So what's that mean? That means that this monic F is sending the empty set of stuff into the E-type elements of B here. So if you look at this equation here, this implies that X of E is also the empty set. And conversely, let's say we knew that X of E was the empty set. Well, that would mean that there aren't any E-type elements of B which have something sent to them under F of E, and that must mean that A of E is the empty set. So these two statements imply each other, and in these cases, if we just set the eth component of R and the eth component of F star to both be the identity function of the empty set, then we will make this triangle commute. when we're thinking about the ETH component, okay? So in that case, where these monics are just sort of sending nothing into our object, things work out well in that case. Now let's deal with the other case, which is the more important one really, the more interesting one, which is where these are not empty sets, okay? So we want this kind of picture, okay? We want these equations to hold for this kind of picture. So we have the ETH component of our monic from A of E to B of E, this f of E here, and we have the ETH component of this inclusion function, and we have the ETH component of I, this inclusion function, I of E. So the only question really is, how do we define f star and r star? Well, it's easy to define f star. We just define its ETH component to basically work just like f of E works. So I mean, if we have an E-type element of A of E, then f of E is going to send that to an element of B of E. But that element of B of E that this element of A of E gets sent to under f of E, well, that's really going to be a member of this subset x of E of B of E, because that's how this subset's defined. This is basically defined as the subset of B of E that has stuff sent to it under f of E. And so we just define f star of E to work just the same way as f of E does on such an element of A of E. So basically f star of E is defined to work just the same way as f of E does. The only difference between these two functions is the target set. This one kind of does its thing, and it leaves the stuff in its, but this f of E here operates on elements, but it kind of leaves them as part of this potentially larger set, B of E, whereas f star of E, it sort of embeds this stuff in a set which is just like as small as it can be. It's just big enough to hold all of the stuff in the images, okay? So basically f star of E is defined on elements just the same way as f of E is. It just goes to this subset rather than this entire set. And so it's quite clear then that doing this inclusion that doesn't alter anything about the elements, it just injects them into this larger set, doing this after f star of E will be equal to f of E. So we have this equation here holding. Now the other thing is, how is this R of E defined? And the short way to say it is that basically we have an isomorphism here, okay? Because for every element B of x of E, there's a unique element of A of E which gets sent to that B under, well, f star of E in this case. So this f star of E here is an isomorphism, and this R of E is the inverse of it, okay? So to say it more concretely, for an element little b of x of E, RE of B is going to be the unique element little a of E such that f of E of A equals B. And I mean, the fact that R is really defined to be a kind of inverse to this f star, and this f star is just a kind of restriction of f, helps one to see that these are properly defined arrows of this category of functors from C to set. So given this R defined in this way, how can we show that this triangle commutes the other way around that we needed to? How can we show that this equation holds? I of E equals FE after RE for an object E of this category C. Well, the thing is that we already have this equation here, that f of e equals I of e after f star of e. And if we just take this equation and compose with r of e on the right, we get that f of e after r of e equals I of e after f star of e after r of e. And now since r of e is the inverse of f star of e, these two cancel to become an identity, and we get this equation here. I of e equals f of e after r of e. And so we have indeed that I is contained in f and f is contained in r, and f is contained in I. And so we've shown that f and I are equivalent. So that's a kind of sketch about how we can consider any monic in this category of functors from C to set in terms of sort of being made out of these inclusion functions. Basically, we can think of monics as just selecting these kind of multi-componented, sort of structured collections of subsets. Okay then, so when we're working in this category of functors from C to set, we have this nice way of thinking about what a monomorphism is, because we can always cook up this kind of subobject x of b, which is equivalent to f, and this associated monomorphism I is basically like an inclusion function. Okay, so we can really, I mean, B here is really a sort of structured collection of sets. Okay, one set for every object of the category C, and these functions between, which we can think of as actions, and we can really think of our monic f as sort of describing this substructure x, which is like selecting subsets of the different sets involved in B in such a way that they're sort of closed under the action. Okay, so doing an action on, let's say, a member of x of E will give a member of x of V, and so on. So we've already seen this, and this is like the characterization of x. Okay, for an object E of C, we have the x of E can be thought of as a set of elements in B of E, such that there exists an A in A of E, such that the eth component of F sends little a to little b. Okay, so basically this is just saying that we can think of x as the load of, we can think of x of E as the load of type E stuff in B that has something sent to it under F. Okay, but I wanted to point out that there's a nice connection here with the Yoni Dilemma and this idea of arrows being in a monic. Okay, so remember the Yoni Dilemma says that an arrow beta from hom E comma blank to B is going to correspond to an element little b of B of E. Okay, a sort of type E element of B. So this is a member of a set, and this is an arrow from one of these hom functors. Okay, so this element of a set, this little b, let's give, like, according to the sort of Yoni correspondence, this is formally related to beta in the sense that little b equals the eth component of beta operating on the identity arrow. And let's give it a name. Let's call it beta dot. Okay, because I like to think of members of sets as like dots, and we take an arrow, we put a dot on top, we get this kind of element of a set that it corresponds to under this Yoni correspondence here, okay? So then we can ask ourselves, we have this expression for the E-type elements of X here, this nice X that represents this monomorphism, this thing that's equivalent to it but easy to think about because it's an inclusion, okay? Well, we can rewrite this as the set of beta dot, okay, so the set of elements little b corresponding to an arrow beta, where we want that this beta goes from HOMI to b. That makes sure it has this kind of form, and we then want the kind of arrow equivalent of this kind of statement, that there exists an element, an E-type element of A, such that f of E of A equals B. Well, to say that there exists a little a in A of E, in Yoni speak, under the kind of Yoni correspondence, putting this in terms of arrows would be to say there exists an arrow alpha from HOM E comma blank to A. Okay, and then to say f of E of A equals B, in arrow speak, that is to say that f after alpha equals beta. Okay, so you can convince yourself that if we sort of take this kind of statement and then we apply this kind of Yoni correspondence, then it'll basically look like this kind of statement here, okay, which is all talking about arrows, but it's saying exactly the same thing, you know, the existence of elements in sets such that certain things composed with each other make other things, and this is just saying the same thing but just describing those elements of sets in terms of arrows. And so if we then say, well, we want the elements little b corresponding to an arrow beta such that this stuff, we get this set here, okay? But what is this? Well, it has a nice interpretation. So we have this object b, and we're interested in the object, and we're interested in the arrows beta into b from HOMI comma blank, and we also have this arrow f from A to B, and we're interested in the beta such that there exists an alpha from HOMI to A, such that beta equals f after alpha. So isn't this just saying the same thing as just saying that beta is in f, okay? Because that's what it means to write beta as in f. It means there exists an alpha such that beta equals f after alpha, okay? So then we can rewrite this to just be saying that it's the set of elements of B of E under Yoni correspondence with some beta, where beta is in F. Simple as that, okay? So this really makes a lot of sense because basically it's like, for example, if you have a graph and you have some monomorphism, okay? So let's say this is a graph and this is a monomorphism into the graph, so it's basically selecting a subgraph. Well then, if you just take HOM E comma blank, let's say this is the HOM functor corresponding to a single edge, and you want to work out is an edge actually in this subgraph, so you can sort of answer that in a arrow-centric way. You can say, well, I have this arrow beta that represents this edge, and yeah, I can find an alpha such that f after alpha equals beta, so yes it is. And then the corresponding, so that would be the sort of arrow-centric way to think of beta as a subobject. But then the kind of element-centric way would be to say, well, we can just think of x here, this kind of inclusion based way of representing this subobject, this graph. We can think of it basically as a subset of vertices and a subset of edges. And does this edge belong to this subset? In other words, is B in x of E? Well, it is precisely when it corresponds with this arrow, with an arrow beta, which is in F, under this Yoni correspondence. Okay, so when we have a beta that's in F in arrow-centric terms, and then we use this Yoni correspondence to go from beta to B, we end up with this element, little b, that we can consider to be in this set B of E, in this kind of construction of x of E. And we make a x of E for every object of our category C, those are going to be closed under action and representing, well, I mean, technically they're representing the source of this kind of inclusion monic I, but really, like x of E is just like a subset of B of E, and the eth component of I is just like an inclusion function. So it doesn't really alter these elements. It just sort of considers them embedded in this larger set. So when you think of this I here, sort of like this inclusion monic is like this sort of canonical way of representing like all of these equivalent monics like F and stuff, so that we're really representing them as subsets. And we can do this because set to the power of C is like this category of structured sets. Okay, so now I told you how to find categorical products in this category of functors from C to set. I feel kind of compelled to tell you how to determine all limits and colimits in this kind of category. Now, I've decided not to actually do that in this video because it would make it too long, but I have some videos in the description box which do this, so I'll talk about that in a moment. One thing I would like to say, because it's quite straightforward, is what the initial and terminal objects in this category set to the power of C look like. Okay, so all finite limits and colimits are present in this category. So there is an initial object, for example. What's the initial object? Basically, it's where everything is empty. Okay, so as usual, we denote the initial object with a 0, and we think of this as an object in set to the power of C, or alternatively a functor from C to set. And all it does is it just sends every object in C to the empty set, and every arrow in C to the identity arrow of the empty set. So, for example, if this was the category of graphs, the initial object would be the empty graph. There's an empty dynamical system. There's, you know, some kind of empty thing in this category that corresponds to an initial object for any category C. So the initial object's pretty simple. The terminal object's pretty simple as well. The terminal object is just a functor from C to set, which we call 1, and it just sends every object E of C to a singleton set. So we'll suppose we have this set capital M, which just has one element, and we'll send every object of C to such a set, and we'll send every arrow of C to the identity of such a set, and that's a terminal object in this category set to the power of C. So for example, for a graph, if we have a graph that just has one vertex and one edge, and the source and the target function are just identities, that's going to be this kind of graph, and indeed that's going to be a terminal object in the category of graphs. And actually the terminal object in the category of dynamical systems is just a single fixed point. It has kind of the same picture, and so you could use this, and I urge you to sort of prove that this kind of construction does give you a terminal object in general in set to the power of C. So okay, that's some of this stuff. So what have we dealt with so far? We've dealt with categorical products, initial objects, and terminal objects. Now I'm about to tell you about the idea of equalizers, which are very straightforward in this category. I mean, basically we just see what entries these kind of arrows between objects and things like this agree on, because they're basically just like these natural transformations that have components as functions. So we can see for a given component which elements those functions agree on, and that defines the equalizer of two parallel arrows. So equalizers are quite straightforward, and this is good because once I've introduced these ideas of equalizers and co-equalizers, we're in a position to understand why things like this category have all finite limits. Why is that? Well, there is a result, which I haven't mentioned in this series yet, but it's a very nice result. And what it says is that if you have a category with a terminal object and with a product for every pair of objects, and with an equalizer for every pair of parallel arrows, then that category has all finite limits. Okay, so somehow there's a way to use those things, terminal objects, products, and equalizers, to construct any finite limit at all. And so the proof to this is a little bit complicated in my opinion. So I didn't want to go through it directly in the video because I've already talked about a different approach to limits in previous videos, which I think is more straightforward. But what I have done is put a video in the description, well actually two videos, where I go over this kind of theory of how to construct limits just using products, equalizers, and terminal objects. And then if one wants to, one can always dualize that kind of approach and figure out how to construct finite colimits using initial objects, co-products, and co-equalizers. I have another video which is linked to, which basically goes over these matters. I mean, I think the best way to, if you're really serious about understanding this category set to the power of C, and all of the things that are happening in there, a very good resource is a book called Generic Figures and Their Gluings, which goes over all of these details. Now, unfortunately, in my opinion, they approach the subject from a slightly, in my opinion, more complicated angle. So it's a little change, but it kind of throws some people for a curveball. Okay, they basically we're interested in these categories of functors from C to set. Now, for some reasons to do with making coherent connections with other subjects and so on, people tend to look at these things from this kind of perspective. They like to look at these so-called presheaves. So when I talk about an object in set to the power of C, I'm talking about a covariant functor from C to set. But what many authors do is they consider these so-called presheaves. So what a presheaf would be a contravariant functor from C to set, or if we like, a covariant functor from the opposite category of C to set. Okay, so there's basically no difference conceptually between these two things. It's just that if you want to work with a presheaf, you want to reverse all the arrows in your category C to start with, and then you can think of your functors being contravariant to kind of undo this arrow reversal. Now, why would you want to do this? Well, just really to match up with the literature, because as you can probably guess from the name, presheaves can be thought of as a sort of generalized version of another concept, which is the idea of sheaves, which comes up. Anyway, my point is that there's this brilliant book called Generic Figures and Their Gluings. It's available online, and it's just all focused on and most of the book is focused on what's going on in this category, and it explains how to determine all these limits and colimits and work with logic and do all sorts of things, but they work in this framework of the category of presheaves. So they basically just switch things around a bit, so they're working with contravariant functors instead of covariant functors, but they're really talking about the same thing. Now, in order to kind of allow people to get into this theory, I made a video on presheaves where I discuss lots and lots of things about them, including how to determine all finite limits, finite colimits, subobject classifier, and exponential objects. Okay, so there's a real lot of information in that video which basically fills in these blanks. Okay, so if you're interested in this stuff, I urge you to watch that video, and then you'll also be in a position after that video where you can easily read Generic Figures and Their Gluings, because I think, like, just personally speaking, I find like the very first chapter is a little bit of a hurdle to get over, to sort of tap into the kind of terminology that they're using. But once you do that, it becomes really a very easy to read book. Okay, so now it's time to talk about equalizers. Now, it's important to understand products, which we certainly had lots of exposure to, and equalizers, because with products and equalizers you can basically build up any limit. Okay, and so an equalizer is the sort of abstraction of this idea of finding out where two kind of processes act in the same way. All right, so in the category of sets, this idea of equalizers is basically this idea of solving equations or finding where two functions act similarly. Okay, and that's because in the category of sets, these objects here would be sets, and the kind of starting place, the diagram that you start with when you want to talk about an equalizer, consists of two, and this is in a general category, it consists of two objects, A and B, with two parallel arrows, F and G. And then in the category of sets, A would be a set and B would be a set, and these would be two functions, F and G. And in this case, this equalizer is basically the subset of A, as described by this monic here. This is a monic, okay, a monomorphism. And this is the subset of A upon which doing F on an element on it gives the same result as doing G on an element of it. Okay, so the basic idea is that we have some set like this one. This would be set A, and then we have another set B like this one here. So in my example, I've got this set of creatures and this set of numbers, and then we have two functions. Okay, so this one here, let's say this is this yellow function here, which computes the number of legs that these creatures have, and let's say this function f in this example, let's say it's this function that sends everything to the number 4. Okay, so I mean the way we cook up these constant functions usually in category theory is we think, well, we'll send everything to the terminal object, and then the terminal object has an arrow coming out of it picking the sort of constant value of this constant function we're trying to make. Okay, so in our example, this is creatures, this is numbers, this is number of legs, and this is constantly 4. Okay, so what's the equalizer then? Well, the equalizer is the set. I mean, this is all in the category of sets. Okay, so this example, I'll talk about what equalizers are more generally momentarily, but let me try and lay some groundwork talking about sets. Okay, so the equalizer then, we can think of it as the set of elements from this set A, which is such that doing F on that element gives the same result as doing G on that element. So in this case, dogs and cats are the only creatures on this list which have 4 legs. So this will be the subset of holding the dogs and the cats. And of course, we'd like to describe that subset using arrows. So we're going to use a monomorphism. And that's going to be really what our equalizer is. So we could think of it like this. We just actually pick out the members of our subset where these two functions are equal. And this would be our set E, capital E. And then we have this monic, which in this case is just an inclusion function. This would be little e. So this is kind of selecting our subset where these two functions are working the same. So that's basically how equalizers work in the category of sets. We'll see shortly that in these categories set to the power of c, equalizers pretty much work this way as well. Okay, they're not much more complicated in these categories than they are in sets. But how is an equalizer defined in general? And it's a very interesting concept actually. It's the idea of equalizers has a big part to play in the sort of theory of toposes, okay, because I mean, one of the main things that you want to study in a topos is monomorphisms, okay, sort of parts of objects, subobjects, and there's a result which says that in a topos every monomorphism is an equalizer. Okay, so we're going to see shortly that every equalizer is a monomorphism. Okay, like in this example, I said we have an equalizer, and it turned out to be this monomorphism here, picking out this subset. So that's one way round, but it turns out in a topos, we can always go the other way around as well. So any monomorphism, basically any part of an object, any subobject, will be a equalizer of some pair of parallel arrows. Okay, right, I'm getting ahead of myself. I need to tell you what an equalizer is in general. Okay, so for general definition. So one way you could think of it is simply as the kind of limit of this diagram drawn in white, okay? So, you know, you could think that we have some functor, which is picking out this diagram in our big category, and then if we take the limit of that functor, we basically have the equalizer. But let me give you a more direct definition, because it's important, and I think there's some benefit to understanding these ideas like equalizers more directly, because it's a nice, small, simple kind of idea that we can kind of use to build up more complicated notions. So what is an equalizer then? Well, we're given, let's say, a pair of objects A and B, and an arrow F from A to B and an arrow G from A to B. Now, the equalizer is an arrow E into A, and it has to be such that F after E equals G after E. And also, it's sort of like the best thing that's like that in some sense, because for any other arrow, C, which is such that F after C equals G after C, we'll consider that other arrow C a candidate when it's like that. We could sort of call it a candidate for equalizing F and G. And for any such candidate, for any arrow C into A, such that F after C equals G after C, we have that there exists a unique arrow L from the source of C to the source of E, which is such that E after L equals C. Okay, so basically it's this usual idea in these universal constructions. We say an equalizer is an arrow into A such that F after E equals G after E, and it's the best one for the job in the sense that for any other arrow that can do that, there's this unique intermediary arrow which allows us to mimic the effect of that kind of phony pretender candidate arrow there. Okay, so that's the basic definition of it. Now, another thing that's true in general, and as I say, pretty profound actually, is that every equalizer is a monic. Okay, so what does that mean? Well, basically, it means that when you have two arrows and you want to find out where they're acting equally upon with respect to an object A, then you're going to be defining a subobject of A. You're going to be defining a part of A monomorphism into A. Okay, and we're used to this kind of idea. For example, when we solve equations, we find these kind of subsets of the number line where two equations have the same values. So we'd say that there's a set of solutions or a subset of the real line, let's say, that are solutions to this equation, that numbers that make F and G agree on when you give them as inputs. So it's a familiar concept in some sense, but it's true in general. Okay, so there's a very kind of nice proof to this. It's a short proof, But I think it's quite clever, really. So what's the proof idea? How do we know that an equalizer is monic? Well, we do the usual first step when we want to show that something's monic. We suppose that we have a couple of parallel arrows, x and y, into the source of this arrow that we want to show as monic. And we usually start with this kind of assumption. We start with this assumption that e after x equals e after y. And then it's our goal to show that x equals y. If we show that this implies x equals y, then we're showing that e is monic. Okay, so how do we do it? Well, what do we know about e? We know it's the equalizer of f and g. Okay, so let's just recall what it means for e to be an equalizer of f and g. It means that f after e equals g after e, and it means that for all c such that f after c equals g after c, there exists a unique L such that E after L equals C. Okay, that's what an equalizer is kind of algebraically. Okay, so this means for all, and this means there exists a unique. Okay, and I use this to mean such that. So okay, let's return to trying to prove that E is a monic. Okay, so we start by saying E after X equals E after Y. So what do we do next? Well, let's just play around with using these two equations. Okay, these give us some things. So if we start with this one and we compose on the right with an X, then we get the f after e after x equals g after e after x. So what does this mean? Well, what this means is that we can consider e after x to be a kind of candidate for equalizing f and g. Okay, so you think that we have an arrow like this that we could call e after x, which is such that doing f after it gives the same result as doing g after it. But also we're supposing that e after x equals e after y. So we also have that f after e after y equals g after e after y from here. Okay, so we have another one of these candidates, e after y, which again can be thought of as equalizing these two. In fact, these are the same arrow. E after x is equal to e after y. So these are the same arrow actually. But now, what does our definition of a equalizer tell us? Well, it says that for any arrow C, like this one, which is such that f after C equals g after C, there exists a unique L such that E after L equals C. Okay, so what do we know then? We know that there exists a unique L such that E after L is equal to our C, which is E after X. But it's also E after Y. So what kind of L could we pick to make this work? Well, we could pick L equals X, or we could pick L equals Y. But there's only supposed to be one that works. So it must be that X equals Y. Because there's only one kind of, like on this diagram, you know, there's supposed to be a unique arrow L, which is such that E after L gives this candidate. But using L equals X or L equals Y makes it work. So we must have that L equals X equals Y. So we started with the assumption that E after X equals E after Y. Now we have that X equals Y. So we're done. So this shows that every equalizer is a monic. And that's a good thing to know because there's a very nice simple way to think about an equalizer as a monic. Okay, so we have this result that an equalizer is a monic, and we also have this other idea, which is that a monic can be characterized by which arrows are in it. Okay, so if we have a monic E and we have another arrow C with the same target as our monic, then we say that C is in E if and only if there exists some arrow L which is such that E after L equals C. Okay, that's just the definition of what it in means, what it means for an arrow to be in a monic. Okay, so I showed, I think it was in the video on special arrows, I showed that a monic can really be characterized by which arrows are in it, in the sense that two monics are equivalent to each other precisely when the same arrows are in them both. Okay, and so it's very fruitful then usually to ask, when you have a monic, what's in it? What characterizes it? That's a bit like asking how the members of a set are characterized. Okay, if you have a set, then what are the conditions for an element to be in your set? This is just the same idea but sort of generalized. So now we know that an equalizer is a monic, we can ask, well, what are the arrows that are in an equalizer? And this is the key result. It's a very nice simple one. Okay, it says that an arrow C with the same target as our equalizer E is going to be in E if and only if F after C equals G after C. In other words, the arrows which are in the equalizer are exactly the kind of candidate arrows for equalizing these parallel arrows F and G. Okay, so how do we prove this? Well, let's go. We assume that C is in E. Okay, so what's that mean? That means that there exists this arrow L such that C is equal to E after L. Okay, fine. But how are we going to finish the proof? We want to show that F after C equals G after C. Well, we do know, because E's an equalizer, we know F after E is equal to G after E. So why don't we compose on the right with an L? And what's E after L? It's C. Okay, so what does this say? It says F after C equals G after C. And that's what we wanted. Okay, so now we have that this implies this. How do we go the other way around? Well, it's quite straightforward. Suppose that F after C equals G after C. What's that mean? That means that C is a candidate for equalizing F and G. And the definition of a equalizer says that there exists, in that case, there has to exist this L such that E after L equals C. In other words, that C is in E. Okay, because that's just the existence of an L that makes this work is precisely what this notation means. Okay, so there we have it, this characterization of an equalizer. So here we have it, an equalizer is a monic, and this simple condition characterizes the arrows that are in the monic. An arrow C with the same target as our equalizer will be in this equalizer monic E if and only if this arrow C equalizes F and G, in the sense that F after C equals G after C. Okay, so we want to understand what equalizers are in this category set to the power of C. And they're really pretty simple. I'll give away the punchline. Let's say we have an object D in this category C. Well, the objects in here are going to be functors from C to set. And so they're going to send this object D to a set. Okay. For example, say we have a couple of arrows like this, F and G, that we want to make an equalizer of. Well, here A is an object, it's the source of these arrows we're focusing on. And we can think of the equalizer as a kind of subobject of A. And the D-type elements of this subobject are just going to be the kind of D-type elements of A, such that doing the D component of F on them gives the same result as doing the D component of A. In other words, if you look at the sort of D component of what's going on in this category, okay, then the equalizer looks pretty much the same as it does in set. Okay, so it's not really much more complicated than that. More interesting though is how we can arrive at this conclusion, because we get to put together quite a few things which we've been talking about. Okay, so how's this work? Well, we already know, so we have this pair of arrows F and G from A to B, and we're working in this category of functors from C to set. Okay, so we already know that the equalizer of F and G is going to be a monic. And we've discussed how when we have a monic in this category, we can sort of find an inclusion monic which it's equivalent to. So this is a kind of special kind of monic where all of the kind of components of the arrows are just inclusion functions. So then we can use more of our intuition about subsets and so on, so it's a nice thing to do. So that's what we want. Now, what is the form of this? Well, I of D is just an inclusion function, including x of D into A of D, okay? And I've already kind of described this form, but just to recap, the Yoni Dilemma gives us this correspondence between like arrows alpha from hom D comma blank to A and elements little a of A of D. So according to the Yoni Dilemma then, say we have this arrow alpha from this hom functor into capital A. Well, that's going to correspond to a D-type element of capital A. An element we might call little a. And To get this little a, we take our alpha and we do the dth component of alpha on the identity, and that gives us this little a. So a good name for this might be alpha dot. Okay, so we just use this notation to represent the kind of element of a of d that this arrow corresponds with under this Yoni correspondence. And I've already argued that when we make this kind of way of representing this monic as this inclusion monic, so it's just this kind of natural transformation I here that has each of its components as an inclusion function, and x here. Well, I've already argued that the form of this x should be such that the kind of d-type elements of x basically consist of the set of alpha dot, such that alpha is an arrow from the Hom functor to a, and alpha is in this monic e that we're trying to represent. Okay, so in other words, if we look at the arrows alpha from Hom d comma blank to the target of e, and we find all of those arrows alpha which are in e, and then we have a load of arrows, and then if we find the load of elements of a of d which correspond to those arrows like this, then that's going to be a subset of a of d, and that's what we call x of d. Okay, but now we can start to use our different results. So one of them is that, well, actually we can characterize which arrows alpha are going to be in e, because e is an equalizer, and we know something about which arrows are in an equalizer. We know that this arrow alpha is going to be in e precisely when f after alpha equals g after alpha. And so we can say that x of d is the set of elements corresponding to arrows alpha from a Hom functor such that f after alpha equals g after alpha. But then if we just translate this stuff from arrow speak back to element speak, which we can do like this, because we know that f after alpha, this arrow, just corresponds to the element fd of a. Well, then this f after alpha equals g after alpha, translated back to element speak, just says the dth component of f operating on little a equals the dth component of g operating on little a, where little a is the element of a of d, which corresponds to this alpha. Okay, so translating then, this just says, so if we do this translation, then we just get that this is equal to the set of elements little a of capital A of d, such that doing f on the little a gives the same result as doing g on the little a. Okay, so all this is what we understand, right? This is just taking the dth component of what's going on, and this is what the equalizer looks like in the category of sets. So after all this, we see that basically equalizers are pretty simple things. We just, if we're interested in the d-type elements of this equalizer, we just look at the dth components of the arrows involved. So these arrows are natural transformations, their dth components are functions, and then we just have something that looks like something going on in set, and we just work out the equalizer of it, the set of elements in a of d, such that doing the dth component of f on it gives the same result as doing the dth component of g on it, and that gives us x of d. Okay, we do that for every object d of this category C, that's how we can construct the equalizer. And I mean, these are equivalent. We might as well consider the equalizer to be made out of these kind of inclusion functions, because it's like a nice canonical way of representing what's going on, and it's easy to think about. Then, you know, what if these things were labeled differently to here, like they might be in here, and we can just think of these equalizers in terms of these kind of inclusion monics. Okay then, so I just want to say, okay, so I want to give a couple of examples of equalizers so that we get the idea how useful they are. So one example is in this category, which is set to the power of this category with two parallel arrows. So in other words, this is an example in the category of graphs, okay, which is a topos. It's something of the form set to the power of c, and each of those is a topos. And in a topos, not only do we have this result, which we've proved in general, which is that every equalizer is a monic, but in a topos such as this, we have the pleasant result that every monic is an equalizer of some pair of parallel arrows. And that means we can literally understand the subobjects of an object in a topos just by thinking about the different possible equalizers of parallel arrows going out of that object. And so here's an example with graphs. It's a bit too busy maybe to be able to read easily, but what I'm trying to illustrate here is that we have two graph homomorphisms from this graph to this graph. We have the red one, which pretty much is just taking this and embedding it here, sending stuffing to everything apart from this edge here. And then the blue arrow from this object to this object is doing pretty much the same thing, except it's folding this directed edge on top of this directed edge, sort of like this, okay? And so then the equalizer of these two is simply the subgraph of this structure where these two mappings agree, which is just going to be these three vertices and these two edges. So this is the equalizer of this red and blue graph homomorphism. Okay. Another interesting example of an equalizer is defining what a circle is. Okay, so in many of these categories there is an object which corresponds to something like a continuum. Okay, so we have natural number objects in many categories, and for example, if you have a category of natural number objects, you can, for example, if you have a topos with natural number objects, for example, the category of sets, you can basically follow something similar to the ordinary construction of rational numbers to make a kind of rational number object, okay? And you can even go further. You can make a kind of object that looks like the real numbers in many cases. You could, I'm probably saying too much here because this isn't essential to what, you know, to what I'm trying to unfold at the moment. But, you know, it is possible to do things like construct a kind of real number object based around ideas like Didkin's cuts or Cauchy sequences. But like I say, I'm not gonna, there's not details I want to get into at the moment, but suffice to say, you can make something that acts like the real numbers in many categories, okay? For example, in the category of sets, of course, there's a set of real numbers, and there'll be various arrows going from that to itself, representing different mathematical operations, functions from the reals to the reals. like this one here that squares a function, like this arrow here that squares a point in the reals and gives another real number. This SQ function here. So we can think of all of this as happening in the category of sets, if we like. And there are other categories which one sort of specifically designs to have very nice, well-behaved kind of objects that look like the continuum, that look like the real line. There's even a category, so-called category of smooth spaces, where one sort of especially picks all of the setup of the category so that one has something that looks like the continuum, but isn't exactly the same as the traditionally studied real numbers. It has some different kinds of properties that make studying continuous things much easier. Okay, but I'm not going to go into that at the moment. So we can just think of this as happening in the category of sets. We can think of SQ as this function that takes in a real number and outputs the square of that number. And these are products, and these are projections. This is a single point. This is a function that sends a set with one element to the number 25. And basically, if we form a kind of equalizer of this stuff, we can think of the result as being the circle of radius 5. Okay, so how does this work? Well, this function here, composing, this just sends a couple of real numbers. Let's say we have a couple of real numbers, x and y. This would be a point of this object. Well, this function sends that pair to 25. Okay, and what does this function do? Well, this sends x and y to well, this purple function sends x and y to x squared comma y squared, and then this, let's say this arrow adds these two together, so we get x squared plus y squared. And so then the equalizer of this function here and this function here is going to be the set of pairs x comma y, such that x squared plus y squared is 25, which is of course 5 squared. So this e here, we could think of this as the set of pairs x comma y, which are reals, such that x squared plus y squared is 5 squared, and this e here we could take to be the inclusion function. Okay, so you see how that's giving us the usual description of this radius 5 circle, the set of x comma y in r squared, I should say, in r squared, such that x squared plus y squared is 5 squared. Okay, so we've talked about products. We might as well talk about coproducts. So just to recap, the coproduct of objects A and B, if it exists in your category, is usually written as A plus B, and that's grouped with these arrows I1 from A to A plus B and I2 from B to A plus B. Now this object A plus B and these arrows I1 and I2 together, they constitute the coproduct of A and B, and these I1 and I2 are sometimes called canonical injections. Okay, now this has to satisfy a universal property, of course, and it's basically the dual to the idea of what's going on in a coproduct. So basically, for any kind of candidate, that is for an object H with an arrow F from A to H and G from B to H, there should exist this unique arrow shown here in green that makes this diagram commute. Okay, so we call this arrow F comma G in square brackets, and we want it to be a unique arrow such that F comma G after I1 is F and F comma G after I2 is G. Okay, so that's the definition of a coproduct. Now, one of the themes that I'm trying to run with in this video is, as I'm introducing these theoretical ideas, I'm showing how we can think about them in this category of functors from C to set. Now, the reason I keep doing this is because we can choose lots of different categories C, and it's a wonderful source of different sorts of universes to see how these different kind of operations look. Okay, and now the coproduct has a fairly simple form in these kind of categories. Okay, so I mean, all of these different types of limits and colimits I'm talking about today, all these finite limits and colimits, they're all present in set to the power of C. And so what do products look like? Well, basically they look the same as they do in set, but there's just sort of a multi-component based version of that going on in this category. So let's say that E is an object of C. Well then, A plus B is an object of this category, so it's a functor from C to set. So if we think about this is, let's say, some of the stuff inside our category C, and this A plus B is a functor going into set. So A plus B of E will be a set, A plus B of V will be a set, and A plus B of S will be this arrow S here, lifted to be a function from this set to this set. Okay, so all we really have to do is describe what kind of sets A plus B sends this object E to, and what kind of function A plus B sends this S to. Okay, so let's start with the first issue. I mean, basically, before I get into the details, let me just say that really A plus B, it just looks like the disjoint union of A and B. Okay, so for example, in graphs, let's say we do the coproduct of this graph and this graph. Well, we can just think of these as sort of disconnected parts of this larger graph. Okay, so this graph where we sort of take one copy of this or one copy of this, we label them differently to make sure there's no cross-contamination, there's no intersection. Okay, so let's say we label everything that comes from A with a 1, and we label everything that comes from B with a 2 on the end. So we make sure that we've really got a disjoint union or discriminated union of these two structures, and then we just consider them together, and that's what we call A plus B. And then these I1 and I2 are basically just these kind of injections which select these two different chunks that this is the disjoint union of. Okay, so that's the basic idea, but how does this work in more detail? Well, we consider for an object E, this set A plus B of E, we consider it to be like set theoretically, it's the kind of disjoint or discriminated union of A of E and B of E. Now, the way we actually make this is we say, well, why don't we stick a 1 on the end of everything that came from here and stick a 2 on the end of everything that came from here, let's say. We don't have to use ones and twos, any distinct symbol will do, but we want to make sure that we're discriminating between stuff that came from A and stuff that came from B. And so let's agree to do that with putting a 1 on the end of these elements A that came from A of E, and we'll put a 2 on the end of elements that came from B of E. Okay, so basically we're just sticking A of E and B of E together and sort of taking their discriminated union or disjoint union. Okay, okay, that's what this set A plus B of E looks like. What do these injections look like? Well, the injections are going to be natural transformations, of course. Let's say we have A in A of E. Well, then the eth component of I1 is going to send this element little a, this E-type element of little a, it's going to send it to A, 1, okay, because this is the sort of collection of stuff, this is the collection of E-type elements of A plus B that came from capital A, all right, the stuff with a 1 on the end. Similarly, the eth component of I2 here is going to send a little b in B of E to B, 2, okay, because such a little b, where that stuff lands in the co-products, we're appending a 2 to mark those kind of positions of stuff, okay. So this is just pretty simple stuff. The idea of sticking two structures together with different labels, and then these I1 and I2 kind of injecting over where the relative stuff got stuck. Now, of course, I'm just describing how co-products work in this category of functors from C to set. I ought to add that, you know, there are many categories with co-products, and, you know, if one goes away from these sorts of nice set-like categories, if you like, one can find co-products which are more complicated, okay. The notion of co-product in a category is not always simply taking two structures and sort of taking the disjoint union of them. Sometimes there's interactions between the two things that you're taking a co-product of in more general categories. But in set to the power of C, things are pretty simple, and basically this stuff looks like disjoint unions of structures. So I've told you how we can construct the different sets involved in A plus B, as in what's A plus B of E for an object E of set. In other words, what set does this functor A plus B send this object E of C to? The other thing we need to know, of course, to know the structure of A plus B is what do actions look like on it. So what happens if we take a member of this set here, A plus B of E. Let's say we take a member A, 1 of this set. And then what about if we want to do this S action on such an element? Okay, so remember we have this arrow S from E to V. It gets lifted to become this function A plus B of S, like so. And if we have an element A, 1 of this setup here, what happens when we do this function on it? What happens when we do this S action on this element? Well, this is what I'm talking about. The thing that we get when we take A, 1 in A plus B of E and do this function A plus B of S on it. Okay, so what do we get? Well, it's pretty simple, really. We just say, well, here's a comma 1. It came from A. We do the S action in A, and then we just take what we got and append a 1 on the end. Okay, so this is the result of doing the S action on little a in this object A, and then where that got sent to under the coproduct. Okay, and then that's what happens if we take a comma 1, something that sort of came from A in this coproduct. Similarly, if we take B comma 2, that's something in this coproduct that kind of came from B, and we want to do an S action on it. Well, we just find a little b, do the S action on that in capital B, and then append the 2 back on it. So we're thinking in this, so we sort of go, okay, lift it back there, look at the source, and then go back there. That's what we want. Okay, so this action is fairly simple. I mean, if you think about it, it's pretty much as simple as it could be in a way. And then finally, there's this question of how f comma g works. Okay, what's the structure of these intermediary arrows? Well, I mean, what do we have? We have an arrow f sending stuff from A to stuff to H, an arrow G from B to H, and so the way that this f comma g works, let's say in set, is it looks in here, it looks at the element and it says, hey, if you came from A, I'll do f on you, and if you came from B, I'll do g on you. Okay, so I mean, imagine we had homomorphisms from here defined, then we can look over here and see which structure our thing came from and do the relevant homomorphism on it. That's basically the idea. And so more formally then, an element of an E-type element of A plus B, we could write it as x comma I, where I is going to be 1 or 2, depending on whether this thing came from A or B. And then when we do f comma g, well, when we do the eth component of it, okay, because it's a natural transformation, so we do the eth component of it on x comma I. Well, if I is 1, in other words, if x here came from A, then we'll do f of e on x, because we know about that f. And if I is 2, in other words, if x came from B, then we'll do g of e on x. And that will be the result we'll get when we do this square brackets f comma g. Well, and that'll be the result we get when we do the eth component of this square brackets f comma g on this element x comma I of A plus B of E. Okay, so that's basically how coproducts work. Again, it's a lot simpler than it sounds, because basically this is just how coproducts work in sets, but then like a multi-componented version of it. Okay, so write down how coproducts work in sets, and then it's pretty much as straightforward a generalization of that as it could be, to understand how coproducts work in this in a category of functors from C to set. Okay, so we have these 4 important types of kind of limits and colimits, which we can use to kind of take a pair of objects and get another object. Okay, so let's recap. We have the product and then the dual idea. So the product basically gives us pairs of stuff. So that's something where we can take 2 objects and get a kind of bigger object out. The coproduct, similarly, that's where we kind of add 2 objects together. Again, we take 2 objects and get a bigger object out, and the coproduct is the dual idea to the product. We also have this idea of an equalizer, where we can take kind of arrows between two objects and use that idea to select a kind of part of the first object. And finally, we have this idea, which is the dual idea to the equalizer, the so-called co-equalizer of a pair of parallel arrows. Okay, so basically, given products and equalizers and terminal objects, initial objects, one can construct any finite limit. So you can do repeated products. So if you want to do the product of three things, you can do the product of two objects and then another one, and so on. And then you can use equalizers, and you can basically mimic any kind of finite limit construction by kind of chaining those ideas together. In a similar way, in a dual way, in fact, you can make any colimits using initial objects, co-products, and co-equalizers. So co-equalizers are an important idea, and like equalizers, they're a way of kind of finding something smaller than one of these objects involved in this case with a parallel pair of arrows. Okay, so remember the case with an equalizer, we're basically able to find the stuff in here where doing F on it gives the same thing as doing G on it, and that's what our equalizer was. Well, the co-equalizer is not a monic into A, it's a epic out of B. And basically what this does is it sort of sticks together things in B. And what stuff does it stick together? Well, the idea is that we look at the stuff in A, and when we have something in A and F acts on it and G acts on it, they may send this thing in A to different places in B, but we always stick those together. So whenever we have something in A, we'll see where it lands under F and see where it lands under G, and we identify those two things in B. Okay, so it's the co-equalizer gives us this basic kind of framework for sticking together stuff in B. Okay, so it's difficult to describe exactly what a co-equalizer is in general. So I'm going to have to resort to a bit of fuzzy language in order to try and get some kind of quick description of it out. But here's the way I like to think about co-equalizers. We have some object B. Now, say we're thinking about this category, one of these categories set to the power of C or something like that, something with a fair amount of structure. Okay, so then we have this object B, and it's got this structure, you know, maybe it's a graph, maybe it's a dynamical system, whatever, or maybe it's a set, and we want to stick some of the stuff inside that set to other stuff inside that set. So how are we going to do it? Well, what we do is we make a couple of parallel arrows, F and G, into our object B, and then whenever we have something in A, that's going to get sent to something in B under G and something in B under F, and then we basically stick those two things together. Okay, so look at this picture. Here is a object B in our category of graphs, let's say, and let's say what we want to do is to stick these two vertices together. We want to identify them. Okay, so what we can do is we'll make another object A with these two arrows, which are selecting these two vertices that we want to identify. And now the co-equalizer of this is basically the same structure, just whenever we have something in A, what that thing gets mapped to under F is identified with what it gets mapped to under G. Okay, so in this case, we stick these two vertices together like so, and this is the co-equalizer, is this object with these things identified and this kind of arrow here, which is sort of sending the structure in B into this structure in Q. Now, the proper way to think about this stuff is in terms of equivalence classes, and I'll get onto that in a moment. But yeah, this is the kind of basic idea of the type of things you can do with quotients. I mean, if we're just working in the category of sets, then all you'd be doing is you'd have a function f and a function g, and those would sort of glue together elements in B that were kind of made by doing an f and doing a g on a particular element in the left-hand set, capital A. Okay. Anyway, we'll get onto this again in a moment. I just wanted to give a rough idea of what's going on with these co-equalizers. Anyway, what's the formal definition? This is the formal definition of what a co-equalizer is in any category. Okay, so we have a co-equalizer of a pair of parallel arrows like this. And so this is basically a colimit of this diagram, and it's the dual idea to the notion of an equalizer. But more particularly, what's going on is this. The co-equalizer of this pair of parallel arrows, F and G from A to B, is this object capital Q with this arrow little q from B to capital Q. And it has to be such that Q after F equals Q after G. So we could say Q co-equalizes F and G. And also for any other kind of candidate that does a similar job, so for any arrow M out of B, such that M after F equals M after G, there's a unique way to kind of emulate this candidate. So there's a unique K such that K after Q equals M. Okay, that's the general definition of a co-equalizer. Now, how does a co-equalizer work in one of these categories of functors from C to set, which we're particularly interested in? Well, basically, it has to do with equivalence relations. So this, again, is just pretty much the same as the description of co-equalizers in the category of sets, but just kind of done with several components, if you like. And so if this is confusing to you, you can start by Googling co-equalizer in the category of sets, and once you've seen that, you'll notice that this is just pretty much the same thing is going on here, except we have multiple components potentially, because this category C might have multiple objects and also these actions, these arrows that get lifted into functions. Okay, so anyway, what does a co-equalizer look like in this category? Well, we're going to have a couple of objects, A and B, and these arrows between them, these natural transformations. And so what we can do is basically just pick an object E in our category C and look at what happens on the kind of ETH component. So what we do, we let tilde E be the smallest equivalence relation on B of E, which is such that doing F on any little a in A of E gives something equivalent to doing G on such a little a, according to this relation which we're defining. Okay, so the way to think of this, or at least the way I think of it, I think it's makes it sound a lot simpler than this, is what you basically do is you think of B of E as a set of dots, okay? And then whenever you have something in A, like let's say an element of A of E, and let's say that F sends it to one of these elements in B of E. Okay, so this is B of E. Okay, so whenever F sends an element of A of E to something in B of E, and G sends that element somewhere, what we think of doing is putting a squiggle between those two elements of B of E. So squiggle E, okay? Or if you like, the way I like to think of it at least is, imagine we're making a kind of undirected graph. So we kind of link these two vertices, okay? And we do this kind of thing for every element of A of E, okay? Every time we have an element of A of E, we see where it goes to under F. Well, okay, this should actually be F of E, and this should be G of E, because these are components of natural transformations, right? But anyway, we do this kind of thing for every element of A of E here, and this is going to build up some kind of a graph. Okay, so this might be one example, and this is fine. I mean, we're thinking about sets here, but that's fine because we're looking at the kind of ETH component of everything. So this stuff, all this stuff is sets. I mean, B of E is a set, A of E is a set. The ETH components of F and G are just functions, okay? So we can form this kind of undirected graph on B of E. And then all we do is we think about what the connected components of that graph is. Because when we say we want this smallest equivalence relation on B of E, what we're basically saying is that we want to have a sort of relation on B of E. So what we want basically, I mean, the technical way to say it is that this tilde E is some equivalence relation on B of E. So that's considered, formally, it's considered to be a subset of the set of all pairs of elements from B of E, which is reflexive, symmetric and transitive, and then we want the kind of smallest subset, which is such that we have this kind of thing going on for every element little a of E. So that's the formal way of saying how we get this tilde E, but the simpler way to say it is just make a graph like this by going over all the elements little a of A of E and drawing undirected edges between F of A and G of A, and then we just think about these connected components of the resulting structure. So if it was this case, it would be like these two. They are the equivalence classes that we're basically kind of partitioning the elements of B of E into, okay? Because basically we're saying that a couple of elements of B of E ought to be in the same equivalence class when, because basically what we want to do is partition up the elements of B of E in such a way that whenever there's a summing in A, whenever there's some A that could like make one under F and make the other under G, then those two ought to be in the same equivalence class, okay? So this is what we want to do. So basically, once we draw in these undirected edges, we can think about the connected components of the resulting graph, and these give us our kind of equivalence classes. This tells us how this equivalence relation tilde E is going to sort of partition up this set B of E into these equivalence classes, okay? For example, if this is little b, then the connected component it belongs to, we could call it the equivalence class of BE, like this, okay? And so in general then, like this whole graph kind of metaphor, so this whole graph kind of idea is my fuzzy way to think about how these equivalence relations and things work, but this is the formal way to talk about it. We'll say that B in square brackets with this E down here, this is the equivalence class of an element B in B of E, and formally we'd say it's vesetable B dash in B of E, which have B dash equivalent to B under this tilde E thing, this smallest equivalence relation with this property, okay? So basically, you can think of this B in square brackets as like the set of all stuff in B. So you can think of this B in square brackets sort of thing as the set of all stuff in B of E that's going to get stuck together when we make Q, okay? Because now I'm going to describe how we actually form the co-equalizer given this stuff, okay? So basically we say that Q of E is the quotient of B of E by tilde E, okay? So that's basically just saying that we think of this Q of E here as the set of all equivalence classes of little b for these elements little b of B of E, okay? So now I can finally describe more formally what's going on in this picture, okay? So okay, I know I keep using this E here, and I mean the things that are getting stuck together in this picture are vertices, okay? So just forget about the fact that E normally stands for edges when I'm talking about graphs. Let's think instead that E stands for the vertices, okay? So I can talk about the interesting thing that's going on here. So what's going on? Well, what we do, we look at A of E, let's say that's the set of vertices of this graph A, and then for every element of A of E, there's only one, what we do is we identify F E of A and G E of A, okay? So we'll be identifying these vertices. Remember, I'm thinking of E as perversely kind of standing for vertices at the moment, okay? So we identify these two vertices, and that's basically what we're doing in this operation. But more formally, I mean, the way we'd say it is, well, we're going to make an equivalence relation on the vertices of this graph, so that it's going to be the sort of smallest equivalence relation we can make, i.e. the smallest number of elements we're going to identify with each other in such a way that for every element of A of E, we have the F of A, we have the F of that element is identified with G of that element. Okay, so what that basically boils down to in this case is just saying, okay, these two things are going to be identified with each other, and this one's going to be left alone. So then, I mean, formally, we'd say, well, these two are going to be sent, these two vertices are going to be equivalent to each other. And so Q here, Q is basically sending an element B in B of E to the kind of equivalence class that it's sent to with this tilde E thing here. So basically, these two things are going to be equivalent, so they're going to get sent to the same equivalence class. In other words, there's going to be a vertex here representing the equivalence class of these two things, and these two are essentially going to get glued together because they're both going to get sent to this vertex here. This vertex is going to get left alone because it's in an equivalence class just itself. Okay, there's nothing else that this gets identified with. And so that's what happens to the vertices in this picture. Okay, so sort of the vertices of this graph Q are like equivalence classes of the vertices of this graph B, where we're identifying two of them when they're both getting sent by F and G from some vertex in A. Okay. So, I mean, basically, we can think of this F and G as sort of telling us how we want to glue together stuff in B. Okay. So that's the story of this kind of system on the vertices. What's going on the edges? Well, nothing. Okay. There are no edges that this F and G are operating on. So none of the edges are getting identified with each other. All the edges are staying the same. But okay, you might ask then, how is the structure of this graph here defined? How do we know what the source and target vertices are of these different edges? Well, that's a question about how the actions work on this Q. And basically, it's answered by this formula here, okay? So remember, this little Q here, the eth component of it is going to send an element B of capital B of E to this kind of equivalence class of B using this kind of tilde E equivalence relation, okay? So let's say we have, let's say, an edge in Q here, and we want to do an S action on it. So in our example of graphs, we'd be doing something like, well, let's think about this edge, okay? We'd want to say, find what the source is of this edge, okay? We'll do Q of S on this edge here, which we'd be writing as an equivalence class associated with some element little b of B of E here, okay? Now I'm switching back to thinking of E standing for edges for this example, but anyway, so how do we do it? How do we understand how this action works on this element, square brackets B of Q of E? Well, what we do is we find a sort of representative, little b, let's say, or anything else in this equivalence class, and that'll be something over here. And then all we do is we think about what the S action is, how the S action works on this sort of little b here. So that would be, in this case, giving us this vertex. And then all we do is we say, okay, where does that vertex get sent under Q? Or in other words, what's the equivalence class that belongs to? So if we have this action S from object E to object V, then we'd want to be doing Q of little v. We'd want to be doing the v component of Q on B of S of B, or in other words, we want to be finding the equivalence class of B of S of B with respect to V in this case. So we do that, and we find the kind of stuff in Q which corresponds to what we get when we do an S action on this kind of element of Q of E here. This kind of stuff, it takes a bit of work to explain the sort of general case, but if you do some examples, draw some parallel arrows in any of these kind of categories, and basically just stick stuff together when there's a common thing in A that gets sent to two different places, then you stick those places together, and that's basically how co-equalizers work in these cases. So in practice it tends to be quite straightforward. So here's one example I really like in the category of dynamical systems. We have this kind of dynamical system that has a state for every natural number, and this update function that sends n to n plus 1. And there's an interesting property, basically the Yoni Dilemma says that we can put the states of any dynamical system in correspondence with the kind of arrows from this counting dynamical system. And what we can do is consider, let's say we have a cycle, let's say it's a cycle of even length, so this is another dynamical system, and what we can do is let's make f to be this kind of function like this, around and round and round. So we're sort of imagining wrapping the natural numbers round and round this square. So that's f. Now let's make another kind of map from here to here, because we're trying to build a co-equalizer. So our other map is going to go to the kind of antipodal points. Okay, so it's going to go like this. So this other map's going to the sort of diametrically opposite states around this cycle. So let's say that's G. So then we can ask, well, what's going to be the co-equalizer of F and G? And basically it's going to have two states, and it's going to be a sort of two cycle like this. Okay, so the way we kind of think of this, here we have an element, so here we have a state of A here in this example, this is A and this is B. So here we have an element of A here, and it's sent to this state under F and this state under G. So these two states are identified, and so we want to be sending them both to the same thing under our co-equalizer Q here, and that same identification is yielded by looking at this state here as well, and then looking at this state here tells us that these two states ought to be identified as well. So we know that those two ought to be identified, and they're both going to be sent over here. So basically we can take this square here and kind of glue it together or wrap it up to make it into a two cycle here, and here this Q here is the arrow of the co-equalizer into this object capital Q. Okay, Now, something to notice, and that's that Q is epic, okay? So we know that the arrow little q involved in a co-equalizer is always epic, okay? I denote epic arrows sometimes with these double kind of arrowheads, okay? This is common notation to show that an arrow is epic. And by following the dual of the argument I gave that shows that equalizers are monic, one can prove that a co-equalizer is always epic. Now there's something a bit more than that that's true when we're dealing with a topos, and a category of functors from C to set is an example of a topos. Now in a topos we have a very nice result, which is not only is every co-equalizer epic, that's always true in any category, but also if we're working in a topos, every epic is the co-equalizer of some parallel pair of arrows, okay? So this is very nice because, I mean, we've already kind of understood how we might go about enumerating the different kind of sub-objects of an object, okay? That's the kind of monic based view. If you want to know what all the monics are into an object, what the fundamentally different ones are, there's a way to do it, okay? But now, knowing this about a topos, let's say we're working in a category like this, we have a way of understanding what all the different epics are out of an object. So the nice kind of thing about this result is it gives us a way to think about the kind of collection of epics out of an object, okay? Because we can put them in correspondence with these kind of parallel arrows, okay? If we think about the different structures we can get by taking different co-equalizers of parallel arrows F and G into B, then that allows us to understand what all the different epics are from B to Q, at least when we're in a topos, okay? This nice feature is not present in all categories, okay? There are some categories where we can have epics which are not co-equalizers of parallel arrows, okay? But this nice feature does occur whenever we're in a topos, like for example the category of sets, or one of these toposes of functors from some category C to sets. Okay, so there's a really nice connection here with coordinate geometry and monics and equalizers and products, okay? It's called the idea of a graph. So let's consider a situation in the category of sets, okay? Let's say we've got A and B as, let's say they're both the set of real numbers, okay? And an f is some function. So it's a function that takes in a real number and outputs a real number, okay? Now, how would we visualize such a function? Well, typically we'd make a kind of plot of it, okay? And we're going to call this a graph, okay? So this isn't graph in the kind of network sense, this is graph in the kind of graphing a function, drawing its values and so on. So this is the standard kind of Cartesian coordinates picture of what values a function takes, okay? So what this picture is showing is that when we pick a value of A, then the height above the given point gives the value of f of A. Okay, so this is a way we can draw, so this is a way we can illustrate a kind of function which sends real numbers to real numbers, okay? Now, the lovely idea is that this kind of notion can just be generalized massively, okay? So firstly, we can ask, well, what is this plot? I mean, we draw these things so often in mathematics. it's easy to forget, what they really are. What is this plot? What is this graph? And I mean, the answer really is that it's a subset of the plane, isn't it? It's a kind of one-dimensional subset of the plane, which is, if we go a certain amount x across, then the coordinates on this line will be at x across and f of x up. Okay, so that's how we can think of this graph. But then we can ask, well, what would happen if these were more general sets? Okay, what if this was the set of dogs and this was the set of legs? What if this was the set of dogs and this was the length of a dog, or something like that? Could we think about a kind of generalized case where these sets A and B are not necessarily numbers? In fact, can we go even further? Could we think that these are just like general objects? What's the kind of most general version of this kind of concept? Okay, so this leads us to the idea of a so-called graph. So okay, now let's talk about general category theory, and I'm going to explain the kind of big generalization of this idea. So suppose we have an arrow f from A to B in a general category. Well, we define the graph of f as this arrow here, which is the identity of A, comma, f. Okay, so that's going to be an arrow from A to A times B, as I've shown here, okay, for this product. So we see that this graph arrow here is an arrow from A to the product of A and B. And also notice I've drawn this kind of tail on the arrow. So that suggests that this is a monic, okay? And it is a monic. It's a monic in general. So how can we see that? Well, let's suppose that we have a couple of parallel arrows, x and y, which go into the source of this graph arrow. And we'll do the usual kind of argument to show that this arrow is monic. So what we're going to suppose is that doing this graph arrow after x gives the same thing as doing this graph arrow after y. And we want to infer that x equals y. So firstly, we can reorganize this. We can just take the x inside the brackets. We can always do this kind of thing. And so then we get that x comma f after x equals y comma y after x. Well, if that's true, and we do p1 after it on the left hand side and p1 after it on the right hand side, those two things should be equal, and that will give us x equals y, which is what we wanted. Okay, so this demonstrates that this graph arrow here is indeed monic. And that's good because once we have a monic, we can characterize it in different ways. Okay, so one thing we can always do is think about what arrows are in our monic. Okay, so we can consider a general arrow, say from an object W. We could call this arrow W1, W2. And we can ask ourselves, when is W1, W2 going to be in 1A, F? Or okay, more explicitly, when is there going to exist a K such that W1, W2 is equal to this graph arrow after K? So that's the question we're interested in, because we really want to characterize what kind of arrows W1, W2 are in this graph arrow. Okay, So this is often a fairly fruitful question to ask when you have a monic is, what are the conditions for an arrow to be in it? And usually this will help you make connections with other things, because knowing the arrows that are in a monic is basically enough to characterize that monic. Okay, so for this arrow W1, W2, we're going to have that this is in our graph arrow if and only if there exists a k such that W1, W2 is this graph arrow after k, and we can sort of clean this up by taking the k inside the brackets and see that this is equal to k comma f after k. Now here's the thing, in order for this to equal this, we have to have that W1 is equal to k. We can see this by composing these things with P1 on the left, okay? So when we say, there exists a k such that this equation holds, well, we know that k would have to be W1, okay? So the only way this equation works, in fact, this equation holds. So the bottom line is that this statement holds if and only if it's satisfied when k equals W1, okay? So this holds true, this whole line holds true if and only if we have that W2 is equal to f after W1, okay? Because we need k to be W1 in order to get these two equal, and if k is W1, then we need W2 is f after W1, okay? So this is equivalent to just saying that W2 equals f after W1. Now we're actually trying to make connections with equalizers, okay? So what I'm actually trying to argue is I'm trying to say that this graph arrow here can be expressed as an equalizer. So the next trick I'm going to do is to say, okay, W2 equals f after W1. An equivalent way to say that is that if we do P2 after W1, W2, we get the same result as if we do f after P1 after W1, W2. Why do I want to do that? Well, you see now I've got the same arrow appearing on the right, and it's the same one we started with. Another way to say this kind of statement is that W1, W2 equalizes P2 and f after P1, okay? So basically, if you think about what's the equalizer of f after P1 and P2, that's going to be a subobject of A times B, and an arrow W1, W2 is going to be in such an equalizer precisely when this kind of thing holds true, okay? So what this argument basically shows is that this graph arrow is just exactly the equalizer of f after P1 and P2, okay? And if you think about it, that makes a lot of sense, because what characterizes the coordinate points that we've sort of drawn white on in this graph, in this plot here? Well, these points are such that if you take the second coordinate, you get the same result as if you get the first coordinate and then do f on it, okay? So we see that this has a kind of geometric interpretation as well. Okay then, so one final result I wanted to mention, because it's going to be useful later when we're talking about toposes, and it's basically something that happens when we have an equalizer. Okay, so Suppose that this arrow E here is an equalizer of these two parallel arrows F and G from A to B in an arbitrary category. Okay, well, it turns out that in that case, these three statements are all equivalent. Okay, so one of these statements holds if and only if the other two hold. Okay, so in particular, I'm going to show that E is epic implies F equals G, which implies E is an isomorphism, which implies E is epic. Okay, so we have a full kind of chain of implication, and if you start with any of these, you could infer the others. Okay, so let's start by assuming then that E is epic. Well, what does that mean? It means that when we have a couple of parallel arrows coming out of the target of E, such as we do with this F and G, we have that F after E equals G after E implies F equals G. Okay, so that's pretty straightforward. To see that this implies this is just direct application of what it means for this arrow E to be epic. Okay, so next then we have that F equals G. So what does that mean? Well, it means that we can draw a diagram like this for the case where F equals G. And of course, this being an equalizer, we have the property that if F after C equals G after C, then there's this unique arrow L such that C equals E after L. Okay, so we draw this diagram, but we set F equal G because that's what we're assuming. So we have this. And then can we think of a candidate C, which is such that doing this arrow after it gives the same result as doing this after it, gives the same result as doing this arrow after it? Well, yes. Using the identity arrow of A gives us something with this property, okay, because F after the identity equals F after the identity. So this identity arrow of A here can be thought of as a candidate, and then we have this unique intermediary arrow L such that E after L equals this blue arrow. So we have that there exists this unique L here such that E after L is the identity of A. But this should seem familiar because this is basically just a definition of what it means for E to be a split epic. Okay, we can think of this L as a right inverse or a section of E. Okay, because it's something that when we compose with it on the right, it yields the identity. So this means that E is a split epic. Now, we also know, as we've already proved, since E is an equalizer, we know that E is monic. So we know that E is monic and split epic. And another result which we've proved in the video on special arrows is that if a arrow is monic and split epic, then it is an isomorphism. Okay, so we have finally got that this implies this. And then it's also true, it's pretty straightforward to show that any isomorphism is epic. So this implies this. So there we have it. All these things are equivalent, and we're going to use this result later because in a topos, the arrows have a special kind of property. It's not true in general, but in a topos, we have that if an arrow is monic and epic, then it's iso. And we're actually going to use this theorem to prove that, but that's in a few videos' time.